Thank you very much. And yeah, thanks for having me at this wonderful birthday event for Tony.
Delighted you're here.
Yeah, so I'm one of the few people here that doesn't actually have joint publication, joint research with Tony, but of course we share the research interest, in this case partially with what I'm doing. And so I thought, okay, I'm going to talk about some of the other stuff that we've been doing recently. And so this talk, this is mostly about entropy indeed, and our attempt to make a kind of a new family of entropy measures, entropy-like measures, useful for the quantification of entanglement and other quantum correlations. So yeah, I'm in Cologne, but it's only recently. That's why I also put here ex-Barcelona. That's kind of when I first heard about this event, I think I was probably still in Spain. Okay, so this is the outline. The first part is mostly pedagogical. So I will basically introduce you to this observational entropy business, because I don't. Well, you probably have heard about it, but under different name and different guise. And then the rest of the talk is about different explorations of this entropy, and in particular its comparison with the phenomenon entropy. Okay, so that's where I want to start. Actually, now before we start, maybe you can't see this down here, but in the recording and in the slides it's visible. This is the archive number. So we posted a rather long paper, I'm ashamed to say, in October with Joe Schindler, who is in Barcelona, and Leonardo Rossetti and Stefano Mancini there in Camarino, where Leonardo is doing his PhD now. Okay, so I start with something that I hopefully is familiar to most people or lots of people here, which is the phenomenon entropy of a quantum state. And so for me, quantum state is always a density matrix. And to keep matters simple, I will always assume that everything is just a finite size matrix. So all my operators are acting on some finite dimension. It's not an intrinsically bad restriction, but at least I can write things like D for the dimension when it actually matters in some of the bounds. Yeah, and this is the formula. So this is kind of famously, it's kind of almost a century old now, minus trace roll of rho. And so, of course, for Neumann, when he introduced this, he didn't do this like in thin air. So he had some very specific physical and thermodynamical motivations. And his justification included this here. I mean, it's more complicated than this, but I'm taking the viewpoint of basically information theory. If you see this here, or if you see entropy, at least at this time, you would have seen already the works of Gibbs and Boltzmann, and well, Shannon came later, but it's the same quantity. In the classical case, when we have instead of a density matrix, just a probability density, this is the accepted formula for the entropy. How can you link this? I mean, the ideal is you want to reduce this to somehow something like that. And so what von Neumann observed was, well, I mean, obviously we cannot really talk about probabilities unless we make an observation. So we talk about measurement. And if it's a maximally how do you say this, informative measurement, so this kind of a rank 1 projective measurement in this time, then the measurement outcomes have some probability distribution. It's written down here. So again, we have the trace formula, trace of rho m1 up to trace of rho md. D, remember, is the dimension. So obviously, if you have rank 1 measurement for von Neumann, these are automatically projective, must be D outcomes. So this is a probability distribution. It has a Gibbs/Shannon entropy. And what he observes is you always have this bound here, and you have equality if you happen to choose the eigenbasis of rho. Or if it's not unique, you have to choose one eigenbasis. And so that was basically, I mean, that is in sort of classical entropy terms, this is his justification. The phenomenon entropy arises as a minimal observational entropy when I make rank 1 measurements. I have to make rank 1 measurements because I could do the opposite, I could do the trivial thing that my observable is simply the identity, or it has only 2 eigenvalues, then the entropy will be 0 or maximally log 2. So I have to somehow force here in this formulation that I have maximally informative measurements. And that was kind of the story in this paper. So he was happy to continue with this quantity, and it kind of shows that it's kind of useful in thermodynamical, to do some basic thermodynamics in quantum states. So I'm interested within the inequality. So in general, we have not equality, but this right-hand side is bigger. And so the conclusion is a general observer will overestimate the entropy. Observer being necessary in quantum mechanics. I hope you, I'm not trying to do a lot of foundations of quantum mechanics, but of course, if we want to play this game of reducing quantum entropy to classical, we have to go through somehow probability distribution. So we need observations, and observations have to be made. I mean, they refer to experiments. And so some experiments, they might be more reasonable to contemplate than others, let's say. So an observer might have some abilities. The access to the system might be characterized to having certain experiments. And if these eigen projections of rho are not available, then maybe this is not a good assignment of the entropy. And so this is an idea that von Neumann actually followed up almost immediately. So it was 2 years later in a paper on the H theorem in quantum thermodynamics, where he talks about such a thing. So he wants to include the measurement, and he wants to make contemplate an entropy that depends not just on the state, but also on the kind of measurement made. And so, and what his motivation there was not so much having a completely different rank 1 measurement, but having a measurement that doesn't give complete information, right? So if you have a, sorry, I wrote this all, but I didn't say it. So what happens if you have a general coarse projective measurement? So the projections are not rank 1, then your measurement doesn't even extract all the available information. This entropy here is bounded by the number of outcomes you have rather than the dimensionality of the Hilbert space. And so his proposal was, let's take a sum of 2 terms. We take the entropy term from the Gibbs/Shannon entropy, and we add an average Boltzmann term. So like this trace of Mi, so these are the projectors. The trace is the rank. It's the dimension of the subspace on which it projects. So this is some kind of a phase space volume. It counts microstates, right? I mean, it's kind of, I guess, most of you again are familiar with this kind of when you go from classical statistical mechanics where we have the configuration space, the cardinalities, they go into dimensions. And we weight this by the probability of observing this outcome R. And so just take the average here. It's very brutal, but it kind of serves the purpose because it includes on one end the maximally refined one when all the traces are 1, then this second term disappears, and we have the previous entropy of the observation. And the other extreme, when the measurement is completely trivial, if you don't do anything, then you get here the log of the identity, so the log of the dimension. So kind of Boltzmann simply log of number of available microstates. And so, yeah, so this kind of thing, I mean, if you look at it this way, nowadays we are not so much wedded to these projective measurements anymore. You see, it makes completely perfectly good sense for a general measurement, a positive operator value measure, where these MIs are simply positive semi-definite sum up to 1. And so I just wrote like a more compact formula that we also kind of use in the paper. So PIs are these traces of rho Mi, these are the observation probabilities, and VI are these volume terms. So I call them volume terms despite the fact that when MIs are not projectors, it's just a trace. It's not really clear what this real number refers to, but formally it's like this. And if you simplify this sum, you get this very nice thing that you have an average over the PIs. Instead of the log PIs, you have a normalized. Say you have normalized PI, so you weight each of the PIs with this volume. And scale it. And so yeah, so this definition, in particular the use of it for general POVMs, that was made popular more recently by Schafranek, Deutsch, and Laguerre in a series of papers starting from about 10 years ago. I mean, they started writing about this, and then very quickly somebody pointed out to them that von Neumann had your formula. So what do you make of this? So well, apparently it's a simple enough idea that it was rediscovered a few times. It depends really what you want to do with it. Yeah, so I wrote it again here. I want to now abundance obsession with projective measurements. We will consider this for arbitrary general theorems. So one of the side effects of this is that, of course, these M's here, these MIs, they could still be rank 1, but they don't have to be projectors. They could be, their traces could be any positive number. And so this volume term also can be in particular less than 1. But of course, they also can be bigger than 1. I mean, the volumes have to add up to D. That's the total volume of the configuration space. So now I want to kind of enter into the mathematical development. To be honest, despite von Neumann being there in the background, when I saw this at first, I thought, well, this is way too ad hoc. I mean, why should I accept such a formula? I didn't like it at all until Joe Schindler, actually, so one of the authors of this paper, pointed out to me, look, oh, I didn't write this. I didn't write this. Okay, sorry, I want to say something. So the entropy of rho, it has this very beautiful, I mean, beautiful but ultimately trivial rewriting in terms of a relative where you need the identity. So in the case of densities on classical configuration spaces, this would be a distribution, or this would be somehow basically the corresponding back measure, some uniform non-normalized distribution. And so I knew this, and he pointed out to me that, look, for the measured relative entropy, we have a similar thing. It's basically just the relative entropy after the measurement. We simply apply the measurement, like so it's a linear map taking the state to a bunch of the probability vector, to the state rho and to this identity. And so formally we get this here. We get this measured, actually I wrote it down here, we get this measured relative entropy between rho and the identity of it. And so I mean, when I saw this, I realized, okay, people had actually already considered these kind of things for a number of years. So like I think the first exploration of this, where not just with a single measurement, but with a whole class of measurements, was Donald in about 40 years ago now. And in quantum information terms and in applications of quantum information, Markovian had a very beautiful PRL about 15 years. Where these, particularly these relative entropies, were made useful in different contexts. And so it's, and particularly the fact that you, rather than evaluating this Omegaki relative entropy on the density matrices, so A and B here are just density matrices, or positive definite matrices, you do it on the measurement outcomes after applying the linear map corresponding. And so, yeah, for me at least, that showed, okay, this is a natural thing to do. This is this kind of not complete insanity, because we know, not least thanks to the work of Nilanjana, that if you can reduce something to a parent quantity like that, a relative entropy, a genuine relative entropy, then most likely we're in reasonable territory. And it has kind of some nice properties. So it's always between the phenomenon entropy and log of the dimension. So this is very important now. So this is something that is for the information theorist in me. This is what this volume term does. So again, remember, von Neumann's motivation was mostly when those volumes are large, when they're larger than 1, because we're sort of lumping together some subspace dimensions. If you want to probe a quantum system, oftentimes you have to do with overcomplete measurements. You have a POVM that consists of maybe rank 1, but subnormalized objects. And the traces are less than 1, but you have more than D. And so a problem of the entropy formula of this term here is that it gets larger than log D. It can be as large as log n. If you have n outcomes, I mean, you could just get a uniform distribution if your state is appropriate, and then this term is log n. And in the case where the B's are less than 1, the second term takes away from that. So there's some kind of spurious information or some spurious entropy that we get rid of again. So that makes this observational entropy different from the Shannon entropy, bounded by the log of the dimension, irrespective of the number of outcomes. Doesn't matter how many So that's kind of cute. And so this inequality, of course, we know this can be sharp because of von Neumann. If we choose the correct measurement, if we minimize of all measurements, we get this vector von Neumann entropy. And so yeah, so in information terms, I think this is something that already you can probably find in the von Neumann paper. Well, clearly in different language, but again, so kind of the information point of view is, well, if you do some post processing, you measure the observable M, and then you do a classical post processing. So that's a coarse grain. You simply let these i's undergo some stochastic evolution. You get a J that defines a new P of M, written like this. Then the observational entropy of the new P of M is largely equal to the old. That makes a lot of sense because you're just injecting disorder. This is kind of not it's not something to do with the state. Yeah, let's come back to this von Neumann equation again. So this is now, like I said, it's a slight generalization because we get this for general P of M's. I should say, well, actually, let me go back a second. Again, I didn't write this, I realized, did I? So the first inequality here is that S of rho is less equal to S dim of rho. You see, because of this formula with the negative relative entropy, this is equivalent to saying that the relative entropy between rho and identity is larger than the measured relative entropy. And so this is a special case of Lindblad's contractivity theorem. The relative entropy goes down under completely positive maps. Yeah, exactly. So we call this in the school information theories, we call it data processing. Exactly. Yeah, okay. So I wanted to stay here. So I wanted to dwell a little bit on the equality case because this will come to haunt us in the second part of the talk. So we need to understand exactly when equality holds. So I told you, okay, fine. From observed, it's enough that you choose the eigenbasis, but in a certain sense, this is the unique solution. So the equality holds if and only if the measurement of the eigenprojections of rho, so if I do the diagonalization with multiplicities, and including also eigenvalue 0 here, because it also has a projection, of course, as a projection kernel. So if this measurement is a coarse-graining of M, that's the if and only if. Yeah, so I stressed here deterministic, which just means that in the post-processing, I'm basically just doing lumping together. So I have my measurement output M here, and what I'm going to do is simply partition the outcomes into groups, and each group corresponds to one of the eigenvalues. And so, well, if you can prove the less than or equal here, it's kind of directly. I mean, you don't need to appeal to the general processing inequality because we're dealing with the measurement and probabilities and so on. So you can use it, prove it directly using the concavity of this function that shows up in the entropy, the minus x log x, and then Jensen's inequality. And so that proves the inequality. And then when you look at the proof, well, because minus x log x is strictly concave, the Jensen's inequality also gives you very strong equality constraints. And so kind of playing around with this, you can extract this condition. Yeah, so in a certain sense, there's a unique solution attaining the entropy of the phenomenon entropy, which is this eigenprojection measurement of rho. So you kind of, I mean, this kind of, I think some people basically say, well, you see, rho is a Hermitian matrix, so you can treat this in observable and just observe this number, and then kind of your outcomes are these RIs, and you project these eigenprojections. And so any other solution is just a fine graining of that measurement. All you do is simply cut up this pi into a sum of positive sandwiches. That's the only other thing you do. Yeah, so another thing that convinced that, okay, it's not so bad is that because we have this relative entropy formula, A couple of years ago already, we published with Joe Schindler kind of uniform continuity bounds for this measured relative entropy. So they look basically exactly like continuity bounds for the for Neumann entropy due to Farnes and Dalitzky Farnes and related quantities, let's say. Yes.
Can you also define a conditional version of it, because you mentioned Dalitzky Farnes?
Yeah, you can. I mean, it's kind of a bit weird because, like classical conditional entropies, it doesn't become negative. So it definitely departs radically from the phenomenon. It may not have ended up in the paper. I mean, I think when we discussed this here, because they prove the continuity, it's kind of the same for the conditional variant. I had some kind of proposal for a conditional measured relative entropy. It may or may not be in the paper. Joe didn't like it so much. And to be honest, I also was a bit doubtful whether it was the right concept. Okay, so let's move on to from one measurement to classes of measurement, because this is what I will need for the entanglement and stuff. So an observer, rather than being characterized by a single measurement, I think it's more reasonable to think of them as having access to a set. I mean, it's kind of, this may be a very crude set and maybe not very easy to characterize, but abstractly we can always associate some kind of set chi with the observer. Or more generally, this could be instruments. So in the archive preprint, we actually, because we want to compose measurements, we actually define everything for instruments, so families of completely positive maps. I mean, I'm basically most of the time I'm not distinguishing for sets of POVMs, especially from sets of instruments. Like instruments for me are just special. Yes, vice versa. POVM measurements are just special instruments. And so yeah, the observational entropy with respect to such a set here is simply the infimum, just in the spirit of von Neumann, right? If we take all measurements available, then we get back the phenomenon entropy. If we take a subset, well, then in general, we will get something bigger. And so again, this is just the the measured relative entropy between rho and the identity now with respect to this set chi. So I just wrote this because these kind of things have been written down before by the likes of Piani and Donald. So yeah, let's skip the activity. Sorry, this is the continuity. Yeah, okay. So there's some interesting things about which sets of measurements you consider here, and it turns out, so like if you want to prove for example, the uniform continuity, you do need some things which are actually quite interesting in operational terms. They have to do, I mean, they tend to be not a problem for those sets that I will discuss in a bit, because those sets are basically defined via they model some operational restriction. And so one of the things that we would definitely want to include is whenever we have a measurement, we include all of its cosgrades. Why? Because we know that this can only increase the entropy. So if our objective is to minimize it, that just gives us more flexibility in talking about the measurements. And it should be closed, this set should be closed under the disjoint convex combination. So I can make a measurement or another one with some prior probability, a flip a coin to choose which of the two measurements I make. And then I remember as a measurement outcome, the coin and whatever the measurement gave. And that's disjoint convex combination. So then we can prove also this kind of continuity bound. So this, like, really in sort of information processing terms, it's a very natural condition here, both of them. And then in addition, if chi is closed under pointwise limits of the POVM elements of the matrices, then okay, so then that means that the S sub chi is actually attained on some element set. Then we can talk again about the equality condition. So S chi of rho is S of rho if and only if this eigenprojection POVM is in the set chi.
Well, this G of epsilon is just the binary entity.
This is this. It's this cousin. The modifier.
Okay.
I think I wrote it on some slide and without commenting.
Wonderful, really.
Yeah. So, but this is more. This comes from the proof. I mean, it's kind of, yeah, exactly. Morally, it's the binary entropy. In the regime that I'm interested usually, but this is absolutely small. It's kind of a binary. Yeah. So how am I doing with the time? Did I say everything here? Yeah. So again, the equality condition. Of course, I need disclosure here. I need the fact that the observational entropy is attained on a particular measurement, because otherwise I can't really talk about the equality. But again, because I'm in finite dimension, because I can always coarse grain sufficiently to make the number of outcomes also bounded, there's really nothing wrong with simply taking the closure. I mean, whenever I have a convergent sequence of POVMs with some fixed number of outcomes, well, it just means that I can approximate the limit arbitrarily well, so I should probably just include it for the sake of mathematical convenience. And so that's kind of what we do for the, again, this sounds like a sort of absolutely ludicrous scruple, but this does happen, you know, in some of the classes that we consider, that maybe we have to consider that they might not be closed, so we have to go to closure.
What do you mean by points-wise?
I mean, I think of the POVM just as a vector of, a vector of matrices, and so like they just converge each of them. Yeah, so this wouldn't work if I allow infinitely many outcomes, but I'll just restrict them. Like all of my measurements are just finite outcomes. I mean, it's unbounded, but fine. Then you have to consider, well, if I allow these coarse grainings, I can actually attain the observational entropy with some number of outcomes that's bounded in terms of the dimension. And so then I can use the comparison. Okay, and so this brings me to our attempt, or rather to Joe Schindler's and Antonio Aguirre and the other guys' attempt of capturing something about the relationship between the state and the measurement, or the measurement class, in this here. And so we know that this difference here is non-negative because of von Neumann, but in general it will be positive. And so like I said, Szafranek, Aguirre, and Schindler, they call this the entropy gap of rho with respect to this class of measurements. And so intuitively, they should capture how much rho is kind of not aligned with the constraint, right? So kind of how much you are failing to implement the eigenprojection measure. So yeah, so then they started making some observations. For example, this gap has kind of some nice properties at least for a single measurement. This is convex in the state, and so because it's a difference of an entropy before and after the measurement, actually when you rearrange the convexity in the form of Jensen's inequality, you recognize this is actually equivalent to Hollywood's information bound of the mutual information after and before the measurement. So it's kind of not a new theorem, it's basically just observation. And so the convexity is just a different expression of the Hollywood bound. Yeah, so some other general properties, so I'm not even going into specifics yet. I'm doing some stuff for general class of measurements. This here is still for a single POVM. So as I said, I'm thinking of a POVM simply as a completely positive and trace-preserving map from a quantum system to a classical system. So I wrote it literally as a linear map from dense images to a vector of numbers. It has a Petz recovery map. So this comes from Petz's investigation into sufficiency of relative entropy, actually. So the relative entropy in general decreases. So he characterized the case of equality. And out pops this recovery map, which exists in general as a function of a state in the CP map. But in our case, our state is replaced by this identity, and our CP map is this measurement. And the recovery map, it looks like this here. It's basically, I mean, it takes in a probability vector, it goes kind of the opposite direction from probability vectors to states. and it forms this convex combination here. And so the POVM elements, they reappear as states, normalized states. And so because of sort of general properties of this Petz recovery map, I mean, so actually from Petz's paper, we have that the entropy gap is 0 if and only if rho is equal to the recovered state, R of M of rho. And in general, we have an inequality that the difference of the entropy and the phenomenon entropy is larger or equal than the relative entropy, the omega-k relative entropy between rho and the recovered state. Yeah, so since Hans talked about this yesterday, note that we have here a fixed point condition. So one should really look at the properties of this map R follow after M, or rather in the Heisenberg picture, M adjoint followed R adjoint because that's the unital, and this will have a beautiful fixed point algebra, which in turn characterizes those fixed point states. Yeah, or rather, well, actually, not just the algebra, but also the conditional expectation you will get from onto this algebra. Anyway, yeah, so and let's leave it here sort of as a connection point to this work of Lindblad, using the fixed point algebra to say something about fixed points of states. Yeah, should I say something? I can say a bit about the future. It doesn't matter. Like I said already, the equality is actually literally from Petz's article. So this part here, this just means that the difference of two relative entropies is 0 before and after a CP map. And the inequality, this is kind of this is more recent stuff. So Fauci and Renner had proved a bound in these terms, but with a different kind of relative entropy. And the one we need here, basically, we have to use that our measurement is that our CP map is a measurement. We have to use the particular simple form of the recovery map, which is basically a state preparation map. Right? It kind of has an option for each I, it can prepare this state, this density matrix, and all it does is make convex combinations. So using kind of some more evolved versions of the Fauci-Renner one, for example, this one here, and then arguing directly by again operator concavity of the log, you can get this. So I leave it at that because I just want to get on with the overview. But it's in the article. Oh yeah, and I cited here. Well, okay, I sort of vainly cited a paper of mine here for the simple fact that what we did here was kind of the classical case. You know, I mean, when the rho also is classical, then the measurement is nothing but a stochastic map. And the Petz recovery map is nothing but another stochastic map in the opposite direction that comes from Bayes' formula. So Petz is kind of quantum Bayes, actually. Okay, so now finally I get to my objective. Okay, let's see. I hope I wasn't too pedagogical and too slow with the first part. I mean, I know how difficult it is to give a talk in an audience like the present one, where we're very diverse backgrounds. I mean, I feel that I'm talking about very basic stuff, and probably a lot of you also feel that. But then on the other hand, I'm probably also using jargon gratuitously and losing half of you just because of this. So if it's too bad, just interrupt me. It might be too late now, but I want to say it. Yeah, so now we want to apply this to composite system, like in the title, entanglement and correlation. So normally you need a composite system to have the density on the composite thing. And our classes should somehow reflect this decomposition. So the simplest ones would be tensor product of local projective measurements. Like for Neumann, but I'm not allowing any projective measurements, but only tensor product of such. Or generally, of course, local POVMs. More modern, so we allow general measurements, but still tensor product. Then comes a class which is one of my favorites, but it's more like sort of a monster. There's LOCC, the local operation and classical communication. So the only way I know how to define it is basically iteratively. It's like, you know, it's like computable functions there is not a one-line definition. You first have to understand the definition of an algorithm. A computable function is those which are computed by an algorithm. And that's kind of the algorithm is a recursive definition. And so LOCC also, we have a recursive definition of an LOCC protocol that involves steps of local measurements, sharing information, doing other measurements. And then at the end of it, we use it to define measurements. And this class is called LOCC. Famously is not closed. You have to actually go to the closure to satisfy one of my axioms. There are examples where we can prove that you need that closure, even for like 3 outcomes. And then another class, so actually I ordered them in increasing generality. Another even larger class is the separable measurements. So that simply means that all the POV elements are separate. And in fact, I could say without loss of generality that POV elements themselves are products, tensor products. And so, yeah, like I said, we have this inclusion here, and in fact, all of these are strict inclusions as sets of measurements. So we have an ordering of the corresponding entropy gaps, because remember, each of these gaps is the observational entropy minus the phenomenon entropy, and we simply minimize over bigger and bigger classes of measurements. And so one of the things we can learn, for example, that might encourage you to think that these numbers have something to do with the entanglement is if the entropy gap with respect to separate measurement is 0, then by the recovery theorem, this means that rho is this here. It's a convex combination of these MRs. And each of them is assumed to be separable. This itself is a separable operator. So these numbers can only be positive if the state is not separable. So this is where the whole program came from. These numbers might tell you something about the entangled character of the state. And so, yeah, in the paper we do a kind of a small another observation. I mean, I call all of these theorems, but I think there are no theorems except for the very first one of Neumann. And even that one, you probably can work it out, afterwards if you have 5 minutes. So it's a lower bound. The separable entropy gap. This is according to the recovery bound is. Well, I have to choose the optimal measurement here. So this is larger than the relative entropy in rho and the recovered state. This is separable. And so that means this is lower bounded by the minimum relative entropy in rho and any old separable state, which is kind of nice because that has a name. That's since the 90s. I think we call this the relative entropy of entanglement. Didn't even put the reference anymore. This is Plenio and Vetral. And so this is one of the best researched entanglement quantifiers that we have. And so it's a lower bound.
You're not just considering bipartite entanglement, right?
Yeah, this is general. This is multipartite. Yeah, of course. I will have some examples where I do bipartite, but I mean up to here it's all general. So yeah, we have this chain of inequalities here, and then the last one is also larger than the reduced state entropy for any subset. And so this X should be any subset of parties, and the phenomenon entropy of rho. So there's also this one, this inequality is kind of general stuff from entanglement theory. Again, I forgot to put a reference. Yeah, I think it's already in the Vedral Plenio article. And so this shows another beautiful thing, which we took a lot of time to prove originally, but that's the simplest way of getting there conceptually. The observational entropy with respect to separable is states of any state is larger than the marginal phenomenon entropy for any subset. Like if you have a bipartite system, there are 2 reduced states, rho A, rho B. The phenomenon entropy of either of them is a lower bound of the observational entropy of the globals. It's kind of nice. And so yeah, let's go to the kind of the good and the bad part of this definition. So like, does it actually really tell us something about entanglement? So the first success story is, okay, for bipartite pure states, that's kind of a domain where we tend to feel very comfortable about entanglement theory. Basically, all the things have been worked out. there is a special role of for Neumann entropy of the reduced state. This is the entropy of entanglement, and this kind of it's a distinguished quantifier that shows up sort of almost inevitably. And this indeed shows up as the entropy gap of all of these guys simultaneously. So they actually happen to be all equal for this class of states. And so in that case, we can say, okay, because we know that this is actually a genuine entanglement measure, it does actually say something about the entanglement of the pure state. Our entropy gaps in this case, okay, they say the same thing. And okay, all I have to prove here, because we have already the lower bound, because this here for pure states, this is equal to the relative entropy measure. Which I didn't say this, but the lower bound is kind of from the previous result. The relative entropy of entanglement for pure state is this here. So I only have to prove the upper bound. So I have to just write, what I do is I have to just find a local measurement to get the same number here, and it's just the Schmidt basis measurement. So just try it out, and that's it. And so another piece of positive evidence is if we consider this LO star, so the projective tensor product measurements. This is also this kind of, because we're comparing a state with the dephased state in a product basis. This can be rewritten also as a minimal relative entropy between rho and any old state in any product basis. And so this has been variously investigated in studies basically of quantum correlations beyond entanglement. So people like Roisman et al., they call this relative entropy of quantumness, because it's zero if and only if rho is diagonal in some specific product basis, which is kind of, that's definitely classical, and everything else might have some kind of quantum feature in their correlations. And so one of the things that, so this kind of reduces to a known quantifier that has appeared in literature, and also the zero case. If the LO star is zero, that means that rho is equal to one of the diagonal states in the product basis, and this happens to be also the same for the general one. So if I'm looking for the gap being zero, LO star and LO, they don't really distinguish the characteristic of the state. Yeah, before I go on, I wanted to spend some time with a caveat. We've seen that these entropy gaps can be related to certain quantifiers of correlations in rho. However, because of their, I felt compelled to say this, because of the appearance of this measured relative entropy, there is a precursor in the work of Piani, but it kind of goes exactly in a different direction. So what he does is he looks at the relative entropy of entanglement. So this is relative entropy in rho and separable state, optimized. And instead of the relative entropy, he inserts the measured relative entropy. So that's in general smaller, so this is upper bounded by the Plenio-Vidal relative entropy measure. And these are definitely entanglement measures with lots of nice properties, which is why he wrote this paper here. So we do something different, right? So we, instead of minimizing here over states, we just put here the maximum mixed state. And then we don't take this number for the face value because it's just an entropy. So we subtract it from Neumann, which is kind of sort of baseline. So, and then we get something which is systematically larger than the relative entropy of Plenio and Vidal. Okay, so what I want to show briefly, and I really see that I'm filling the hour after all, I want to show that in this chain of inequality that we observe, every inequality actually may be strict. We can construct examples to separate those measures. So there's not gratuitous. The difference in the classes of measurements actually reflects in different values here. And so the first one, there are different ways of doing this, but I mean, for me, the simplest one is we take a so-called CQ, a classical quantum state. So the one is a bipartite state where one system is just in a orthogonal basis state, and the other one is in some mixed state. Could be, well, actually, in the example, it will be a pure state, and we can have arbitrary probability distribution. So when you look at the observation entropy here, it's fairly fast, fairly soon you find out the best measurement is the obvious one you measure in the given basis here. And so that's why this class of states is nice. It basically reduces to find the optimal measurement here. And so you can write the observation entropy of the tensor product of the x and of the general M measurement as the entropy of P, because that's what we get from here, plus, so this is distribution, plus the observation entropy of the reduced state rho B, so this rho B is just the marginal, observed with M, minus a Shannon neutral information. And so if we assume that rho B is maximally mixed, which we can easily engineer like as a separate condition on our ensemble, then this term is log D. So we have the entropy of P that's constant, log D is constant, they are just given from the state, minus this mutual information. So since I want to minimize the observational entropy, I need to maximize the mutual information. In fact, this has a name. This is the object of Holevo study. This is accessible information. We're given a bunch of states, make the measurement that maximize the mutual information. Holevo already knew that projective measurements are not as good as general measurements. So a concrete example is this one here. Take the uniform distribution of these three states in qubits, so the equiangular states in a qubit. There's sometimes called trine or the Mercedes star, Mercedes-Benz star states. So then this here is h of, this is log 3 plus log 2 minus this mutual information. And we know actually what the optimal measurements are among all possible measurements and among projective measurements. And those are the numbers here, and they're clearly different. So this is clearly less than that one. and so that is one of the examples. And from the principle, you can see you can generate lots and lots of examples. It's almost generic. This difference here is the same state, actually, because these guys are non-orthogonal to each other. And so by LOCC, I can just measure x, and then knowing x, I know the state of the other side, so I can just measure in its eigenbasis. And I get that the gap is 0. For all of these states, the entropy gap under LOCC is 0, because I can sort of describe a measurement that involves a bit of classical communication between the parties that reaches the von Neumann entropy. And we've seen before that the entropy gap under local measurements is actually some number that is positive by inspection. This also is, that's a really nice Q separation. Actually, I think we were ready to release the paper when we eventually understood how we do this. And again, it's cute because it uses the equality case. So we construct a state that has separable entropy gap equal to 0. And it goes like this. So if we go back to a very beautiful old paper by Charles Bennett and many other people, they construct a particular orthogonal basis in 3 by 3 that consisting of product state. But it's not a product basis. So it's not a tensor product of two bases. It's just that each vector happens to be a tensor product. Whatever, I mean, this is going to be important for the second part, but since they are product states, so the projectors are product projectors, these form a separate measurement. So I can just, whenever I form a convex combination of these orthogonal pure product states, if I use the alpha k tensor beta k measurement that is separable, I get entropy gap equal to 0, right? Because the entropy is simply that I observe is simply the von Neumann entropy, sorry, the Shannon entropy of the P distribution, which is the same as the von Neumann entropy. However, the LOCC gap must be positive. And so the reason why we know this is because of the difficult results from the Bennett et al. So what they show is that this measurement here cannot be implemented by LOCC. In fact, it cannot be even approximate. Remember this story about the closure. So you actually need to prove that there is some epsilon such that all LOCC implementable measurements are always at distance at least epsilon from this one. But on the other hand, if the entropy gap were 0 for LOCC, that would mean there is some LOCC implementable measurement, or rather a limit of such, that gives me this one. Yeah, so basically, I mean by this equality condition. If I get 0, I mean the equality condition of von Neumann's inequality. And so I know that this measurement is actually implementable by LCC. And it's contradicting the main result of it. And so the final inequality, that's the worst one. Actually, I saved it for the end. Actually, it's very easy. So this one, again, we can make an example where this is 0, but this is positive. So what this means is that I'll show you that I want to convince you that there are separable states where nevertheless the E sep is positive. And so, for example, I mean, the recipes take any separable row that has a non-trivial kernel, such that the kernel projection is not separable. It's an entangled operator. And so, then the E sep is positive again by this equality condition theorem, and the relative entropy of entanglement is 0. So examples include, for example, the fully symmetric state in D cross D, so like for example, the triplet in 2 qubits, or a very cute class, subtract any rank 1 projector from the identity in D cross D and renormalize. That's always separable for every entangled person. But the orthogonal complement is psi, and it's entangled. So yeah, this last thing, it means that these ELOCC and ESEP, they cannot be regarded as entanglement measures in the sense of the axiomatic theory. Now here I have the reference of the Horodetsky's, this kind of big review article. So the main thing that they fail is the monotonicity under local operation classical communication, because they are 0. These measures are 0 for some separable states and positive for others, and I can go from one to the other by LOCC. Anyway, it's still good for bipartite pure states, and I'm hoping that they're also good for multipartite pure states. And so I wanted to show some examples, but I realized I really used up my time. So it turns out, so this kind of hope that these kind of numbers are well behaved, it works out for this very simple multi-party entangled state, because they're kind of like bipartite. GZ type means that you simply have a superposition of these kind of equal basis states. Then we generalize the bipartite pure case, so all of those entropy gaps are equal to the entropy of this distribution of the amplitude modulus square. And we get a lot of mysterious things for another class of very nice multi-party entangled states, the so-called W states. So we basically in each of the n systems is a qubit, and you have this uniform superposition of almost all 0 in a single one somewhere. And so we can't actually calculate this even for n equals 3, but numerics suggest that these local and LO star gaps are log n, and the evident the evident measurement is the optimal. We just measure in the local computation basis. The problem with proving it is kind of this highly non-convex optimization problem. So kind of you would need some ad hoc inequalities, and we just didn't go there, to be honest. So what we did notice is that the LOCC and the separable gaps, they are strictly smaller than log n already for 3, even though I mean they're bounded away from 0, from 0. And I think for separable, they don't even scale with n, they go to Wechsler constant. And so this is my last slide. I just want to sort of wrap it up. So like for me, I mean, posting this paper on arXiv, especially it's so long, is sort of a bit ambiguous, because we started out with this program, okay, let's investigate whether this entropy gaps tell something about entanglement. I mean, at some point through the development, you realize, well, I mean, they are not even monotones. I mean, after decades of research by the likes of Horodetsky and so on, I propose something which fails the very first axiom. There is kind of a good part. It seems that for pure states, at least, it's fine. So that's not very interesting in the bipartite case, because it just reproduces this one quantity that we already know. But for multipartite systems, there are plenty and plenty of entanglement monotones that relate to entropy. So for example, in an old article by Noah Linden et al., they observed that the reduced state entropies of any group, of any party and of any group of parties, that's a monotone for pure states. If you know that you're going from pure state to pure state, this can only decrease under LOCC. And so maybe these entropy gaps are monotones for pure states, which is kind of nice, because for multi-party entanglement, a lot of investigations focus from the start on pure states. And so then there are plenty of other questions like this one here. I really have nothing to say about it, but it's a very important question. Are they additive under many copy tensor products? I mean, my hunch is probably not, because in quantum information, nothing is additive, but you can always hope. Okay, and with that, I should probably stop. Yes, thank you very much.
First of all, thanks, Shane, for organizing this event for Tony's birthday. So I think I met Tony first when Joe and Tony were visiting EPFL, and I was a postdoc there. And then one summer, I remember, you all came over, and you came over, and we had extended discussions with maybe Nicola and Philip on Bose-Einstein condensation. But then when I moved to Cambridge, Tony visited, and we ended up working a lot together, and very enjoyable collaborations, and lots of papers on quantum information theory, and an amusing paper on, do you remember, spread of epidemics, the only paper in applied probability. Yeah. COVID. Yeah. And he's been a good friend and collaborator for many decades. And for those of you who don't know, he's also a very accomplished dancer and an artist. And one of his paintings adorns my office in Cambridge. So happy birthday, Tony. Yeah. So this is work done with my former student. Oops, I wanted to borrow. Satveer Singh. Do you have a physical? Okay. But doesn't matter, it's low enough. So who's now a postdoc in Munich, and Nilanjana Datta, who is now in Sweden, and the paper was just published last week in the journal called Quantum. Okay, so I'm going to be very, very basic to start with, because we need to. All right, so systems and relevance in quantum information theory, as you know, are generically open. So here I schematically denote an open quantum system A, that is block here, and it's open in the sense that it has unavoidable interactions with the surroundings, which I denote by E, and as you know, E is often called the environment or the path. So what we're interested in is the time evolution of an open quantum system in the so-called weak coupling limit. So that is the limit in which the interaction between A and E is weak, in the sense that decay times of correlation functions of the environment are much, much smaller compared to the typical time scale over which A's state changes significantly. And in some sense, A forgets about its interaction with A, E forgets about its interaction with A, and returns to its steady state quickly relative to the speed at which A evolves. Yeah? In that sense, it's the weak coupling limit. And in this limit, the dynamics of A becomes Markovian. And it is mathematically modeled by what's called quantum Markov semi. So the focus of this talk would be on A undergoing a discrete-time Markovian evolution. And our information theoretic task is to encode information in the system A in such a way that it can be recovered perfectly. That's with zero error, even after A is left to evolve for an arbitrarily long time. And so A can be viewed as a quantum memory in which we store information so that it can be perfectly retrieved anytime in the future. That's our goal. Okay, so mathematical setup. So H is a Hilbert space associated to the quantum system A, and throughout this talk I will take it to isomorphic to CD, where D is finite. Okay? D-dimensional complex space. And L of H will denote the set of linear operators acting on H. And of course, it is isomorphic to the set of D cross D complex matrices, which I will just denote as ND. And you already heard about density matrices, quantum states in Andreas's talk, which I denote by D of H, positive semi-definite and of unit trace. And I will also sometimes refer it as SD as a subset of MD. Okay, so much so for the notation. Now, any allowed physical operation on a quantum system, including its time evolution, is most generally given by what is called a quantum operation or quantum channel. And so this is a map from the set of operators H to possibly the set of operators on some K, some other finite infinite space. But it is given by, you already heard in law, completely positive trace preserving map, which is the acronym CPTP. So just for those who don't work on quantum information theory, let me put one slide to justify why we need what is meant by complete CPTP and why we need it. So firstly, a simplification. Also this talk, the channel, the quantum channel, will go from L of H to L of H. So the two Hilbert spaces are identical. And now let me justify why you need the map to be linear, completely positive trace preserved. So first, it's very easy to understand why it should be positive and trace preserved. Now that can be seen like this, because if you take a quantum state and you send it through the channel, what comes out is this. And what should this be? This should be another state of the quantum system, and therefore it should be positive semi-definite and of unit trace. In other words, phi therefore should be positivity preserving and trace preserving. Okay, but now what about this complete positivity? What does that correspond to? Well, that comes from the fact that, as I said, we are in general dealing with open quantum systems, right? And now say we are looking at a state of this composite AE system. And we want to do some operation only on A and do nothing on E. Yeah, this looks like this. So phi is, say, the quantum channel or quantum operation. This acts on the A part and nothing. This is the identity map. Yeah, nothing acts on the E part. So what happens when this acts on the composite state? It should again be a valid quantum state of the full AE system, and therefore it should be also positive semi-definite. And this should be true no matter what environment we consider. So any linear map phi which satisfies this condition for all E is said to be completely positive. So that's why we end up with a completely positive trace preserving map. Okay, there is a very useful theorem which gives us a representation of the phi and does not depend on just system, and it doesn't depend on what environment we choose. So it says that there exists a finite set of linear operators. Also, this talk I will take this set as ki's, i's ranging from I to finite r. These are linear operators such that the action of the channel on rho is ki rho ki dagger. Okay? And because it is trace preserving, that amounts to ki dagger ki summed over all I being equal to the identity operator. Very easily seen by taking the trace and using cyclicity. And now the Krauss represent operators, the set of Krauss operators is not unique, but different sets of Krauss operators are just related by a unitary transformation. Okay, so one important thing to point out that quantum channels are in general noisy. So what comes out of the channel is in general different from what goes into the channel. And so this is important because information encoded in a quantum system when sent through the channel is distorted because of this noise in the channel. Okay, so we are going to consider, as I said, evolution of the system A governed by a discrete time quantum Markov semigroup, so which is denoted like this. So where each phi is a quantum channel, and by phi n, I mean the n-fold composition of phi n stuff, by acting successively. So this is our key quantity. So schematically, it can be represented like that. So the input goes through one action of the channel, then sequentially second, third, fourth, etc. And this phi n, so this satisfies the semigroup property. Yeah, phi n composed with phi n is phi n plus n. So this therefore forms a discrete quantum Markov semigroup, which I denote as DQMS. So here n plays the role of the time parameter. And the task to repeat once more is to store information in A, which acts as a quantum memory, so that it can be retrieved perfectly. And because of this picture, this amounts to perfect transmission of information across time. That is through phi n, n being the rate of time. Right. And now what we are interested in is zero error communication through this quantum Markov semigroup. So let me start with something which I call one-shot zero error classical communication through just phi before we go to phi n. So this is the picture. So suppose there's a sender called Alice, say, and has a set of classical messages. And in order to send the message M from the set, he encodes it into a quantum state. Why? Because between her and the receiver Bob, there is only a quantum channel. Okay, so this rho M goes to the channel, out comes this state, and now Bob gets this state, but Bob wants to infer Alice's message. So as we saw on the last talk, we have to do measurements. So you do the measurement and say M prime denotes Bob's inference. And here M was the set of classical messages. Now, one shot. Why? I call it one shot because only one use of phi is allowed. That's why the name one shot. And zero error because Bob should be able to infer Alice's messages perfect. That is with zero error. And of course, we are sending classical information. So what do? We require that M prime is equal to M. Now, Alice wants to send all these N messages. When can she do that? She can do that if and only if she can encode them in some set of quantum states such that when they go through the channel, phi rho M is orthogonal to phi rho M prime whenever M and M prime are different. So these are mutually orthogonal states. And that all of us know is because in quantum mechanics, only mutually orthogonal states are perfectly distinguishable. So if Bob gets states of this form, he can distinguish and infer the messages without ambiguity. Okay, and of course, as you all know, when I use this notation sigma orthogonal to omega, that means trace of sigma omega is equal to 0. Okay, so this allows us to define something for the capacity of phi, a one-shot zero error classical capacity of phi. It's very simple. It's just the maximum number of bits that can be transmitted perfectly over just a single use of the channel. So this is the notation I use: zero error, 0 here, C for classical information, classical capacity, and 1 for one shot of the channel phi. It's given by such an expression that we go stepwise. Whenever we take log, as in the previous talk, we always take log to the base 2. And what is C? C is collections of states going from 1 to cardinality of C, such that when each of these states go through the channel, they are mutually orthogonal, because then you can distinguish between them. Yeah. So it's the largest logarithm of the largest cardinality of states, which can be distinguished after their passage through the channel. And it can actually be shown that these rho m's are what? Rho m's are the encoding states. You take your message M, you encode them in rho m, and you can take them to actually pure. But there is another convenient definition of this one-shot zero error classical capacity of phi in terms of something called the operator system S phi of the quantum channel. These things are all studied by Andreas and his co-authors long time back. Okay, but just for concreteness, let me tell you what is this S phi of a channel. So it's defined in the following manner. So suppose this denotes the set of Krauss operators for the channel phi, then it is just a span of ki dagger kj. Yeah? Okay, so what is this? Firstly, notice that when you take a sum of this form, by the definition of the Krauss operators, we know this is identity. Yeah? Clearly, this belongs to S of phi. Secondly, it is easy to check that if X belongs to S of phi, then its dagger, transpose of its complex conjugate, also belongs to S of phi. So S of phi is therefore a closed subspace of the MD closed under this dagger operation. And such a subspace is called an operator system. And S phi is independent of the chosen Krauss representation, since different Krauss representations are just related to unitaries. So, okay, this is just a mathematical definition, but how is it relevant for transmission of classical information with zero error through a channel? To answer this question, let us ask the following simpler question. You have a channel phi, I want to use it once, and I want to see when is this one-shot zero error capacity positive. So when can you send at least one bit of information? So we saw this was possible if there exists two pure states such that when they go through the channel, they are orthogonal. Yeah? And what I'm saying is this is equivalent to another characterization, that if we take the outer product of nu with psi, then this operator is orthogonal to what I defined just now for the operator system. So let me prove this very simple fact. So this is what we want to prove, that one equivalent characterization of the one-shot zero error capacity being positive is there existing two states psi and nu such that outer product is orthogonal to S phi. In the Hilbert-Schmidt sense, where this is S phi. Okay, it's really simple because what do we need? We need that the outputs corresponding to these inputs are orthogonal. That means the trace of their product is zero. And then it's really trivial because phi acting on psi acts like this for a quantum channel. So all I'm going to do is I'm going to write phi psi and phi nu. Okay? And then what am I going to do? I'm just going to use the fact that psi is written as an outer product and nu is an outer product. One line of calculation gives us this expression and use cyclicity of the trace. So what does this imply? This has to be zero, right? In order for us to distinguish. So this tells us that for every ij, this quantity has to be equal to zero, right? And how can you write this quantity? This quantity can be written in this following form. This reduces to this just by taking cyclicity of the trace. So in other words, this tells you, if you look at the definition of S of phi, this tells you that this outer product must be orthogonal to this space in the Hilbert-Schmidt sense. So we have this characterization of the zero error one-shot classical capacity being positive. Yeah? Let us use this characterization to define another way of defining equivalent definition of one-shot zero error classical capacity. What one does is one defines something called the independence number of S of phi, alpha S of phi. What is that? It is just the maximum size k of a set of pure states such that this condition is satisfied whenever m is not equal to m. Yeah? And this is, of course, the maximum number of different messages that can be sent through with zero error through a single use of the channel. And when we want to talk about capacities, we take the log of that maximum number. So here we have a characterization of the capacity entirely in terms of the operator system. And the word entirely will become very relevant to us as the talk goes on. Okay, that was classical information transmission, but a quantum channel, unlike a classical channel, can also be used to transmit quantum information. And so quantum information is encoded in states of quantum system, and we can also consider one-shot zero-error quantum communications through phi, which then amounts to perfect transmission of quantum information through a single use of phi perfectly. Yeah, one-shot zero-error. Okay, so what is this? I will primarily focus on the classical communication, but let me, for completeness, just give a couple of slides here. So suppose an m-dimensional quantum state can be sent perfectly through phi. When can it be done? If there exists some subspace of the Hilbert space with dimension s equal to m, such that there exists a recovery map, which again is an allowed quantum operation and so has to be a linear CPTP map, such that we also saw a particular recovery map in Andreas' talk, so that when rho is acted on by the channel, then if you do this recovery map, you get that rho. Yeah, you want to get your whole state rho now, because that's the quantum state. So in other words, this is what happens schematically. And if you look at that box, which is phi composed with rho, it effectively acts as an identity map, because in comes rho and you get back rho. And so the largest dimension of a subspace of that form, where you can define a rho which so such that you get back rho, is therefore so therefore the quantum capacity will be the logarithm of such the dimension of that, such that there exists a recovery map, and you take a supremum of all such subspaces of the underlying space. So heuristically, it's just the maximum number of qubits, because they're taking log to the base 2, that can be transmitted perfectly through a single use of the channel. But ultimately, we are interested in the quantum Markov semigroup. So we are not interested in communication through phi, but through phi n. Yeah? Now, triviality, but worth noting that if phi is mapped from LH to LH, so is phi n. because successively every phi gives a state back in LFH. Now, if you're interested in transmission through phi to the n, the big picture that we saw before changes a little bit. Instead of just sending it through one use of the channel, you send it through the successive uses of the channel. Out becomes phi n factorial over n. But I put this all in a green box just to stress that therefore n successive uses of phi amounts to a single use of phi n, which is also a valid quantum channel. So that's why we're talking about one shot through phi n. Yeah? And we want n prime to be equal to n, therefore it's zero error communication. Okay, now our focus is on one shot zero error communication, classical for quantum through phi n. Now let us first say what would we naively expect. So you have using this noisy channel n times. Yeah? So successive actions of phi on the quantum system in which you've encoded the information and sending it through first channel. As you are using more and more channels, these add more and more noise to the system. So naively, one would expect that any noisy quantum channel would ultimately, for large enough n, become useless for perfect transmission of information, right? More and more noise is added. So eventually, as n goes to infinity, you won't be able to transmit anything perfectly. However, surprisingly, somewhat surprisingly, there exist channels which retain their ability of perfect transmission, no matter how large n is. So how long you let the system evolve. So these are the questions that we ask. First look at the ones which do become useless eventually. So what are these channels? How can we characterize channels for which there is some n, such that for n larger than that capital N, the one-shot zero error capacity of phi n is equal to 0. That's the first question. So such channels become, as I said, eventually useless for perfect transmission of classical information. And what happens? You can think about it that the noise in the channel is such that it scrambles the information which is sent through it, so that perfect recovery is impossible for large n. So this was the first question. So for such questions, for such channels, it is interesting to ask what is the minimum number of users needed for the capacity to become 0. Okay, so this is the picture. Suppose you use the channel successively n times. After n users, you can still send some information, but say after n plus first, it becomes 0. So we want to find what this minimum bad number is. So this minimum number in this schematics is just n plus 1. So this tells us this minimum number of users needed to make it useless, we call the classical scrambling index of phi, terminology coming from classical information theory. So we want to find which channels are useless and how many repetitions or concatenations are needed for it to become useless, which is the classical scrambling index. Okay, then the most interesting thing. So if the channel becomes useless, that means it's limiting one-shot zero error capacity 0. So this tells us channels which are not in this class must retain their ability to transmit information perfectly for all n. Yeah. So this tells you what for such channels this limiting capacity must be positive. And this brings us to the third question, that for such channels, what is not useless channels? What is this limiting capacity? Can you find an expression for it or a bound for it? And we ask the same set of questions for the quantum communications with phi n. Won't go into detail, but I'll just use one slide. What are the channels for which the quantum one-shot capacity becomes 0? And then for such channels, what is the minimum number needed for it to become 0? And which we call the quantum scrambling index. And finally, the channels which are not in this class, they retain their ability to transmit quantum information perfectly. And so what is the limiting value of the one-shot quantum capacity? Okay, so these are the questions. Okay, answers to our questions. So first question, what are channels phi which become eventually useless? So this is the theorem. So here, the channels which become useless, so for which there exists an n, so that this one-shot zero error capacity becomes 0 for large enough n. if and only if the channel is mixing. What does that mean? That means there exists a unique density matrix, unique state, such that no matter what x operator is acted on by the channel, in the limit, you just get trace x times rho. Okay? So in particular, if you take x itself to be some state, yeah, normalized state, so then this trace x is 1, and so you get this relation. So no matter what you input through that line of users of channel, ultimately you get back the state rho. Yeah? So such a channel is said to be mixing. And of course, you heard about fixed points in the last talk. So this rho is of course a fixed point of the channel. So no matter all the pi's acting on it, you always get rho. Okay. So mixing channels are ones which have become ultimately useless for sending classical information. This leads to our second question. For mixing channel, how many users do you need for the capacity to become equal to 0? Okay, and what we find is this classical scrambling index, the minimum n needed for it to become 0. We find an upper bound on it, which depends on the dimension of the underlying Hilbert space and the dimension of the operator system. This is what we find. And a key ingredient in proving this upper bound is the following fact, which is stated here as a lemma, that for any such discrete quantum Markov semigroup, the corresponding operator system, so there is an operator system corresponding to phi squared, phi cubed, etc. These form an increasing chain of subspaces. So the S phi is strictly included in S phi squared, and so on and so forth, which stabilizes at a time n following this, where n is upper bounded like this. What does that mean? There's strict inclusion until you come to S of phi n, and then it becomes equality. Yeah? So all these therefore stabilize. Now are the same. Yeah, operator systems are equal. Why is this very important? Why is this the key to proving that inequality? Yeah, about the scrambling index. So this is the reason. The implication is, so as we saw, the one-shot zero-error classical capacity of any channel, and in this case we consider phi n, yeah, is just given by the logarithm of the independence number of that corresponding channel. So the capacity is entirely given by the operator system. So therefore, if the operator system stabilizes in this time, then the corresponding capacities will also stabilize, right? So what does that mean? That C01 phi n plus 1 is equal to C0 phi n for all small n, yeah? Because n is the value at which it stabilizes. So this is the key. So we want to see how to prove it. So this is what we want to prove, that the classical scrambling index, minimum time needed for mixing channels to have 0 one-shot capacity, satisfies this inequality. This is extremely simple because remember, for a mixing channel, it becomes ultimately useless. So this limiting value, the stabilized value of the capacity is 0, and stabilization happens after this time. That means so after these, the capacities all become 0, and so C of phi, the minimum n needed, can be at most this one. Yeah. Okay. Now you can answer the same questions for the quantum case. What are the quantum channels become eventually useless? These are what's called asymptotically entanglement breaking channels. So let me just quickly tell you what one means by this. So if you have a channel, you have, let's say, an entangled bipartite entangled state, A prime, rho A prime. You do nothing to the system A prime, and the system A is sent through the channel. Yeah? And what you get at the output is sigma A, say A prime B. Say the channel takes you from A to B in general. So a channel is said to be entanglement breaking if no matter what state you put in there, the output state is always separable. We heard of separable states in the last one. And what our theorem says is that a quantum channel, which ultimately has 0 quantum capacity, one-shot zero-error quantum capacity, is one which is asymptotically entanglement breaking. Roughly speaking, this just means that phi n is entanglement breaking in the limit n. Okay, and how many compositions are needed for this capacity to become zero, which we call the quantum traveling index? I won't go into its proof, but it is exactly similar. It is given by upper bounded by d squared minus the dimension of the operator. So, but let's come to the most interesting question. Those are mixing channels are useless for classical, zero error classical communication. For non-mixing channel, this is the interesting question. What is the maximum rate of information transmission with zero error? So first, let me tell you a very simple example of a channel which is not mixing. So henceforth, we're looking at not mixing channels, channels which retain their ability for perfect communication of classical information. So very, very simple example is the following one. You have just a qubit channel, yeah? And so it's a max N2 to N2. So this is orthonormal basis of C2. What the channel does, it takes 0, 0 and maps to 1, 1, and 1, 1 to 0, 0. And it just annihilates the other states. So if you take a qubit density matrix like this, of course, under the action of the channel, these will be swapped and these will be additive. So first, in order to be, let's look at every channel has a fixed point. Let's find this fixed point. Just using these two relations, we can find easily that the fixed point is just identity over 2, so half. Okay. So this turns out to be the unique fixed point of this channel. Okay, but we have to show that it's not mixing. So what does it mean by not mixing? That when you input anything into the channel and take n to infinity, then if it goes to this fixed point, then you would sort of say it's mixing. Yeah, but we can see that's not the case, because what does the channel do? It swaps zeros and ones. So if you take k concatenations of the channel and act on 0, you would get 0 for k even, but you would get 1, 1 for k odd. Yeah. So in the limit n going to infinity, you see it just fluctuates between 0 and 1, and you do not get it converging to I over 2. So this condition, which is the requirement for a channel to be mixing, is not satisfied. So phi is not mixing. Okay, so it's not a non-empty set that we are talking about. So we have non-mixing channels, and then we can ask what is its limiting this one short zero error capacity. And similarly, we could have asked for a not asymptotically entangled breaking channel, what is the one shot quantum capacity? Okay. So in order to answer especially this question, in fact both questions, we need to recall something about the spectrum of quantum channel. So a quantum channel is a linear map, right? It's from MD to ND. Okay, and to any linear map, we can associate in the usual way the spectrum, which is complex numbers such that this is not invertible. ID is once again identity. So in other words, it is the set of complex numbers such that there exists an x in MD such that phi x is lambda x. Okay, so these are the known facts about the spectrum of a quantum channel. One can look, for example, excellent book by Wolf. So the spectrum of the quantum channel is given by a disk in the complex plane. Okay. And unit disk. So all the modulus of all the lambda are less than equal to 1. And the eigenvalues are symmetric with respect to the real axis. So they are either on the real axis or they arise in complex conjugate pairs. So if lambda belongs to the spectrum, so does lambda. And lambda equal to 1 is always an eigenvalue.
The spectrum is contained.
The spectrum is, yeah, you're right. Typical Tony, yes. Contained, yeah, not equal. Sorry for that typo. Yeah, so lambda equal to 1 is always an eigenvalue. So they're always equal to rho such that phi rho is. This follows from something called Brouwer's fixed point theorem. So rho is the invariant state of the fixed point of the channel. So every channel has a fixed point.
Just a question. So you're only looking at the finite dimension.
Yeah, everything.
Because every finite dimension is.
We're all talking about finite dimensions. Okay, so we will be particularly interested in what's called the peripheral spectrum of the channel. These are just the eigenvalues which lie on the periphery. Okay, each peripheral eigenvalue has a unique multiplicity. By that we mean, there's the notion of geometric multiplicity and algebraic multiplicity when we write out a channel in terms of this nilpotent form, etc. Yeah, you know what I'm talking about. As lambda I. These are the projectors and the values, and these are the nilpotent parts. So anyway, each peripheral eigenvalue, but then one can talk about the number of. Anyway, let's not go into that. But these two, there is a unique notion of multiplicity, and this peripheral space of phi. What is it? It's just a span of all those operators, such that phi x is lambda x, but with the modulus of lambda being equal to 1. So that's why I said it lies on the periphery of this unit disk. And the structure of this space is very well understood. Okay. Now, why am I talking about the peripheral space of the quantum channel? What are we wanting to do? We have a channel which is not mixing, and we want to use this channel successive times, such that, so you want to encode information somehow such that this information is preserved no matter how many times the channel acts. Yeah? So the claim that we make is for zero error communication. It suffices to encode information in states that lie in the peripheral space of the channel. Yeah? So let's look at it. So this is the definition of the peripheral space, right? All those x's which satisfy this lambda equal to 1. Now there is this very nice theorem. You can find it in books, for example, in the channel's notes. For any phi quantum channel from LH to itself, there exists a decomposition of the underlying Hilbert space in this form. This is a direct sum of tensor products, such that there exists such a decomposition and a fixed set of quantum states which only act on this Hilbert space. And these fixed states are also positive, not just positive semi-negative, such that any x in the peripheral space has the following form. So any x in the peripheral space can be written as a zero direct sum with xk delta k. So these delta k's are these fixed states, and these xk's are just operators which act on this form. Okay. I'll carry this over to the next slide. So this is the peripheral space, and I say any x belonging to the peripheral space is of this particular form. Xk's only act on the hk1 part, and therefore it is a dk1, dk cross dk matrix, where k is the dimension of hk1, and delta k are fixed. So this is a very well-known theorem. So let us look at the non-trivial part. So it's a direct sum of tensor products, so we can write it, ignoring everything else, we can write it as x1, delta 1, x2, delta 2, etc. Remember that delta 2, delta 3, etc. are fixed states, and these states are of different dimensions because x1 is of dimension d1, x2 of dimension d2, etc. Okay. Now, I said that for zero error communication, it suffices to encode the information in states that lie in the peripheral space of the channel. Let me justify why. Let us see why this claim is true. To answer the question, we would need to know what is the action of the channel phi on states or on operators which belong to this peripheral subspace. Yeah? So operators of this particular form. And it is known, that's also another theorem, that phi acts non-trivially only on the x states.
So is the second tensor factor the HK2?
HK2.
What they, no, HK2, the second tensor factor, is that what they call in the literature noiseless subsystem, or noiseless subspace?
No.
No? Because the second factor is not effective, right?
The second, okay, but I don't know the name. Andreas, do you know this noiseless subspace? I never heard of this noiseless subspace.
There's decoherence-free subspace, and then there's noiseless subspace.
Okay.
And my understanding was like when you have this decomposition,
Yeah.
and you can factor it, then the second tensor factor.
Yeah, then in that sense it is noise. I just not familiar with the terminology. But so everything non-trivial just happens here on this. Now, and not to confuse it. So what happens here is the next question, right? What happens here? What does the channel do? It just permutes these xk's of the same dimension. So there are all these blocks x1, x2. Those which have the same dimensions can be permuted. So pi is some permutation matrix. I'm going to show it again in the next slide. And it acts, they could be acted on by unitaries. I've drawn a simple slide to convey this fact. So this is the part which is affected non-trivial. As you notice, these delta ones, etc., get not affected. So just for simplicity, forget the delta ones. Just let's look at x1, x2, etc. So the action of the channel is like this. What does it do? It can permute blocks which are of the same dimension. Yeah. So suppose it permuted. So x1 tilde is in this case x3, x2 tilde is x5, etc. So this is the permutation. And something else that is possible, that there a set of unitaries exist for which the x1 hat now becomes uk dagger xk tilde x uk. Yeah, so there is a permutation and then a unitary. So in other words, what does the channel do? It shuffles the blocks and acts on them by unitaries. But actions of unitaries and permutations all can be undone. These are noiseless operations. Yeah, so you can. Therefore, the action of the channel does not distort any information which is encoded in these blocks. Yeah, because of what I just said. So, if we encode information in the blocks, then they remain shielded from noise for an arbitrarily long time. Because no matter how many times pi acts, it's just permutations and unitaries which can be undone. And we don't have to do this forever because we know there is the time n bounded by d squared minus the dimension of the operator system after which things stabilize. Okay, so how should we encode classical information? So we answer this by saying that encode them in the diagonal elements of these matrices xk. Because you can encode d classical messages in a d cross d matrix in the following manner. You take the ith message and encode it in the basis element I. Yeah. So d classical messages in a d cross d matrix. So the number of messages you can encode in this capital X is therefore summation of dk, where dk was the dimension of xk. So you can, if you encode messages in the way I said, then the total number of messages you can encode such that they are preserved forever, yeah, with zero error, is this. So the corresponding capacity, that's the number of bits of messages which you can preserve forever, is log of this number. And so this must be the expression for the one-shot zero error classical capacity for these non-mixing channels. Okay, and lastly, what? So this is just stated as a theorem for a channel pi which is not mixing. This is the expression for the one-shot zero error classical capacity. And where remember this non-trivial part is here, and this is what you call the noiseless. Okay, last question. How should we encode quantum information? If we want to really send information, quantum information, we don't want to just encode them in diagonal elements. We want to send the full quantum state, which is a matrix. So you want to transmit a quantum state, which is given by a matrix. So what is the maximum amount of information? It is just the size of the largest matrix, which remain unchanged. What is the largest matrix you can transmit without distortion? Therefore, a matrix of size, maximum of k, dk. Dk is d1, d2, or the individual. So this tells us the maximum number of qubits transmitted perfectly to pi n, as n going to infinity is the logarithm of this quantity, which is therefore 4 channels which are not useless for transmitting quantum information, which I said were these channels which are not asymptotically entanglement breaking. This is the value of the capacity. So this is stated as a theorem for a channel phi which is not asymptotically entanglement breaking. This is the amount of quantum information that you can store in the quantum memory to go back to our original picture for arbitrary amount of time, in which you will later. So to summarize, so what we considered was to encode information in an open quantum system A, whose dynamics is governed by a discrete quantum Markov semigroup, such that the information can be retrieved perfectly in the future. And this was therefore a study of one-shot zero-error communication through this discrete quantum Markov semigroup. And we found that the channel becomes useless for classical communication if it's mixing, existence of this unique fixed point such that all other states converge to it. And in the quantum case, it is what is called asymptotical entanglement breaking. And for both these cases, we evaluated the minimum number of compositions needed for the capacity to become zero, which we call the standing indices, classical and quantum. And we found upper bounds in terms of the dimension and the dimension of the corresponding operator system. And else, that is for channels which are not useless, oops, too fast, sorry. I'll thank you, but in a minute, in a second. So for non-mixing channels, it is given by the logarithm of some of the blocks in this decomposition, and similarly for quantum communication, for non-asymptotically entanglement breaking, by the logarithm of the maximum dimension. Thank you for your attention and for the thanks to my co-authors and Lisa.
Thank you. So first of all, I would like to thank the organizers. Shane, thank you. Tony, thank you for the invitation. It's a pleasure for me to be back in Dublin after more than 10 years. And I would also like to thank Tony because he was a great supervisor when I was postdoc at Dorlas. And I remember actually our Friday seminar where we actually spent time proving the theorem, some theorems, but not just proving the theorem, but finding the best way, the more meaningful way to prove the theorem. And so what I've learned from you is that it's not just proving that is important, it's not just the knowledge, it's how you get there, get to this knowledge. And so I hope I do the same as a teacher, and so I would like to thank you for that, and wish you a happy birthday. Okay, so today I'm going to talk about a difficult question, time in quantum mechanics. I would like to propose an alternative formulation that I call operational, operational meaning measurement, therefore protocol, and stochastics, which is a mathematical description of this protocol. And I will show you, I decided to show you the application to time, the time of arrival problem, but there are also different applications to, such as optimization of transfer in quantum computing, for example, with some different methods. Okay, so why is time important in quantum mechanics? Because there is a theoretical gap, first of all. So Pauli in 1933, I found a paper actually, and this is a footnote. He said that for a semi-bounded Hamiltonian, there is no self-adjoint operator T, so that T and time and H commutes and equals I over H bar. Actually, in Pauli's paper, we use Hermitian instead of self-adjoint, but because at that time the difference was not clear. But what he meant actually was self-adjoint. So time is not unobservable in the usual sense. And as he said in this note, this is an external parameter. But that's a problem because it's difficult to define and observe, for example, the time of transition between two energy levels in an atom or two spins, or the time of arrival when you drop an object, for example, and you want to know at what time the object will reach the detector. How do you define that time? And also, experimentally, how do you, if you don't know how to characterize time rather than using an external parameter, how do you construct the time distribution? And therefore, how do you calculate the mean value of the time, the standard deviation of the time? There are different approaches like quantum speed limit. I will mention that. Okay, but this is not based on the time distribution. So there is no projective measurement to measure time. I will say a little bit more about that later. Therefore, there is no way to reconstruct the statistical distribution. Okay, so there are, fortunately, different approaches with pros and cons. So the page router mechanism, which is an interesting way to answer the question, what is time? Basically say that it doesn't answer what is time, it just said the universe is timeless. So this is not more like what is time is not. And they say that time emerges as relational variable encoding the correlation between the clock, which is a part of the subsystem, sorry, and the system itself that you want to study. Well, okay, that's fine. The problem is that this is not really operational. Okay, so we cannot measure anything. And also there are some difficulties that makes the model not completely reliable. So this is why the quantum clock model is a little bit more interesting. So Mathieu and Seth Lloyd, etc., work on this problem. Because time is represented by the state of an auxiliary quantum system, which is the clock as well. And basically there is a pointer state, and you know what is time by measuring the state of the clock. However, the clock has to be entangled with the system, which is very difficult to do it experimentally. Okay, and so there is no experimental measurement so far that has been done. And they have actually a recent proposal on time of arrival as well, which is based actually on the protocol very similar to the one I will introduce after that. And actually they use this protocol to build their own protocol, but we found different predictions because their protocol is slightly different. But this is based on the same idea, and I will tell you after what it is. Time of arrival. First thing we do is semi-classical. So you drop an atom, and what do? You just measure the time, thinking that the trajectory is classical, which is often the case experimentally. Actually, this is always the case. So they make this assumption that the motion in this direction is classical. Therefore, they just do basically a classical measurement of time. Time of flight is one of the techniques. Well, it's good, but if we want to observe some quantum effect, it doesn't work, of course. It fails. Okay, and I will show you that some effects that are quantum will be interesting to know, but they cannot measure it using their protocol. POVM, so we talk a lot about POVM. So POVM is one of the, so Kijovsky, for example, proposed that idea, is one of the cool, I would say, proposal. The problem is that it works only for free particles, restricted to positive momentum. Therefore, if you have, for example, a quantum backflow, you cannot describe it, and also free particle only. And this is also difficult to realize experimentally. And if you do with some lasers, then you interact with the particle when the particle is moving anyway, so you have some quantum, the protocol is invasive. So you don't really know what is the time because you interact with the system is moving anyway. Absorption has the same problem via complex potential, which is a very old proposal by Alcock, and Muga did more recent update. Same thing, you have a protocol, so you have an absorbing protocol, potential, sorry, but if the potential is very large, then the particle reflects, so you don't measure it. And if this is too weak, then you may not measure it. And anyway, because you interact with it all along the path, then this is, you can either freeze the dynamic because of the quantum zero effect, and this is what happens when the potential is too large, or you can simply decohere the state. There are some self-adjunct also, despite what Pauli said, you could build in some circumstance self-adjunct operator, but it works only for very specific cases. The Beaumian approach as well, so you consider classical trajectory to describe quantum trajectory, as you know by the Beaumian formulation, but this is non-operational, there is no protocol to measure it. So they get a formula that actually very similar to mine, the one I will show you after, but they don't have a protocol. So as we can see, oh yes, the first detection protocol is not to measure time of arrival, but mostly to measure the transition between states. So it's based on discrete time projective sampling. So again, projective sampling. So that means you repeat the measurement like a T1, T2, etc. Then you can freeze the dynamic, the Zeno effect, if you interact with it weakly, or you can decohere. So this is an invasive protocol. So you don't really get a distribution that reflect what is the real evolution of the system. By real, I mean the evolution of the system as if you were not interacting with it. So key limitations, there is no, as far as it goes, there is no experimentally accessible time framework that unifies both discrete continuous system that applies to all dynamics and not invasive. So that's the goal. The goal is to find an operational formulation. So a protocol from which we can reconstruct the statistical distribution, and that is contextual in the sense, like, as you see, transition between two energy level or time of arrival are two different times. So there is no just one universal time, there are different times. So it depends what we want to measure. So it has to be context dependent. And unifying framework in the sense like we want to do discrete, continuous, as I mentioned before, systems. So that's what we want, okay? So this is ambitious, but in the same time, you have to release the universality of time. It's not like the universal that we described, it's more like a time for each measurement that we want to do. And that's based, I asked myself these questions when I read this Henri Poincaré old paper published in 1898, La mesure du temps, the measure of time, where he actually anticipated the general special relativity theory by saying, before we answer the question, what is time, we should first ask the question, what do we measure when we talk about time? Okay, so the concept is time of flow distribution. I will explain why I call time of flow distribution. And as I say, it's an operational, and I will show you that this is stochastic. So basically, what is the plan? The plan is first to know what we measure. 2, find the protocol. 3, the mathematical description of this protocol via a stochastic approach. Then 4, a couple of mathematical results to find the properties of this time of flow distribution. And then some new predictions so that we can eventually one day verify it experimentally and see whether this is good, valid, or not, or even useful. Okay, so this is based on 5 articles actually, but the 2 most recent articles, the second one was published last week as well. So same thing, good timing. So one was published a couple of months ago, the other one last week, as they say, where I basically these 2 papers generalize the former papers that I published on this topic. They are more general results. Okay. Yeah, I gave QR codes because this is friendly. Anyway, okay. So let's move up. Okay. So before I explain the protocol, I would like to build an analogy, and I call it the airport analogy. Not that I like airport because I spent the night yesterday to travel, but I think it's a good analogy. So imagine you are working in an airport, you are managing part of the airport, like a gate, the gate 8, and you realize that you never have enough employees, okay, because there are some peak time, okay, sometimes there are a lot of passengers, sometimes less, etc. So you say, okay, I have to do something. So I'm gonna hire a guy, like the engineer that I call quantum engineer, you will understand after. And this engineer would like, actually his goal is to find the time distribution, so the time of flow within the gate, okay? So how do you do? First protocol, you can say, okay, I'm gonna count the number of passengers in the gate that are sitting in the gate, okay, and waiting for the plane to leave. And then I look at the evolution over time. And then when I look at the evolution over time, I will just normalize it in order to make a probability distribution, and I will be able to calculate the probability that the passenger will arrive through the gate, in the gate, between 1 p.m. and 5 p.m. The other solution, which is a little bit simpler, is that we have like gates, security gates, and there is a detector, and we measure directly the current, and we know how many passenger goes through the gate every second. Okay, so that's simple. You see the analogy now. The gate A2 is the quantum state, okay, where you want to measure the time of flow. The guy is a quantum engineer. Protocol A, you count the number of people, and then you see how many people live, and go by calculating the finite difference of the population. The gate is basically a current operator, and that's it. Okay. So what we try to do now is to reproduce the same idea and to build a protocol for quantum systems that reproduce the same thing. The difference is that you cannot measure values. I mean, you can measure using continuous measurement or repeated measurement, but if you do so, you can freeze, as I say, the dynamics because of the zero effect, or you can decohere the state. So the best thing to do, and that was the trick actually that was, I think, interesting for Mathieu and Lloyd, is that you prepare the state at t equals 0, you let it evolve through the dynamics, and then you measure, you use a projective measurement, but I realized that you could use POVM, actually, any measurement that you want to do, at a given time, tk, for example, t1. But you switch on your detector only at t1. You don't switch it on before to avoid the interaction between the detector and the system. And then you repeat the same thing many, many times in order to build statistics and to know what is the population in the subset of the Hilbert space corresponding to this projective measurement. Okay, and you get nk. Okay, and then you do the same thing, you repeat the same loop for any time. So T1, T2, T3, etc. So there is a lot of measurements, I agree, but this is the only way to avoid the protocol to be invasive. Okay? And then you calculate the difference, the finite difference. You divide over delta t, where delta t is the sensitivity of the detector. You normalize it, and then you get this bar graph, which corresponds to your distribution. Okay? So that's very important to understand that you switch on your detector only at the time at which you want to measure. That means you have to do a lot of measurements. It's true, but this is the price to pay. So that's basically what I say. That's the protocol. Okay? That's so the frequency. So which corresponds actually to the probability for the state to be in the subset of m at the time tj in that case. And then when you take the limit, so mathematical construction, second step, we take the limit of ideal detector, infinite size sample limit, and then you find simply that this distribution equals the normalized value of the absolute value of the rate of change of the probability distribution in the subset of M, which is a simple formula. Okay. So sometimes in quantum physics we call this dt PM the rate, simply the quantum rate. But in that case, it's not just a quantum rate, which is used for quantum speed limit. This is a normalized quantum rate, and this, in this case, you can interpret this quantity, and you understand it maybe using the airport analogy as the probability of flow within the state between 2 times T1 and T2 when you integrate this probability distribution. Okay, so that means it will tell you what is the odds for the state to be populated during that time. So that means for the state for the particle to move in this state. So it's not the probability for the particle to be in this state, but to go in this state. So to arrive in this state or to depart from this state, depending on the sign of this quantity that we can interpret as the current, or as the current within the state. So the L, the L is the Lim-Lagrange superoperator because it works for any dynamics closed or open quantum system. And so because now we can reconstruct time distribution, there you are. We can calculate the mean value, the standard deviation. Okay, so that's it. So again, back to the interpretation. So how does it work? For example, if you want to measure the transition between two states, then you just use the projective operator that is kk, okay, so bra k, k, or you could do also in a subset of the Hilbert space. And for continuous system, you can simply integrate between two eigenvalues of an operator A. Imagine you want to measure the time of flow between AI and AF of an operator A, then you use a projective measurement that project in the spectrum of A. We assume, of course, that A is a self-adjoint. And there you are, you can calculate. So, the nice thing, if you remember at the airport, I promised you two protocols. A, by counting, this is what I did, and B, by using a current operator. Well, what you could do is that you could rewrite the time of flow distribution by using this adjoint of L, okay, which basically for closed system is simply the commutator of H and M multiplied by H bar, and that gives you the analog of a current operator for moving particle in space. And I will show you later that it is actually a good analog. Anyway, so if you measure this operator, there you are. You calculate the average value of this operator, the mean value of this operator, and there you are. You get your time distribution. Okay, so that's protocol. Okay, so a simple example, two-level system. So sigma x, the Hamiltonian, sorry. The initial state is a quantum superposition. The target state is 1. By the way, the current operator is proportional to sigma y. So that means if you measure sigma y instead of sigma x, you do a bunch of measurements, you get direct access to, you can directly reconstruct the time distribution of this transition. And then you can build it, okay? Show it, right? And then what we realized that there are two regions, the time of departure and time of arrival. Departure is when the population decreases, arrival when it increases. So you can change your the time at which you monitor the system in order to find either the average time of arrival, the average time of departure, or the average time of flow, which is both in that case. Okay. Another interesting, this one is more interesting, Hadamard dephasing model. So imagine you have this is the Hadamard gate, and the Hamiltonian is proportional to that. So Hadamard gate basically is a gate that will flip 0 to plus state. But too bad, we have also a dephasing model, which is often the case in reality. Then we can find the current operator of the system, and we could measure directly reconstruct the time of arrival, in this case this is time of arrival because this is always increasing population, and then we can, thanks to that, imagine you measure that experimentally, then you can see how fast the state is moving from 0 to plus, and you could also find the width of the distribution, which is related to the standard deviation, etc. So you can basically use this as a way to improve your protocol. For example, if you can have a different type of protocols, you could, for example, change omega to omega t and change omega t so that you do the transition as faster or before, etc. And also a more spread out or narrow distribution. Okay, so this is, it gives you like a way to engineer the transition. So, also notice that as you increase the value of gamma, the distribution is narrower, which makes sense because there is more dephasing. So this is consistent with what we expect. Quantum bound, time uncertainty bound. So of course, if I tell you I have a time distribution, you expect me to tell you something about the time energy uncertainty principle. Okay. So first of all, we can do it, but we have to change a little bit the mindset. So now we have a time distribution. A distribution. So what we should do is to use probability theory, okay, and not operator theory first. And so what I found in the recent paper is that using the Chebyshev inequality, which is basic inequality, we can find that the standard deviation is bounded below by the knowable constant, this is the best I can find, times 1 over pi max, okay, the maximum value of the distribution. It makes sense because it's a distribution, probability distribution, so the area is 1. So of course, if you increase the maximum value of the distribution, you will your distribution will become narrower. Okay, and so that gives you like a lower bound. Okay, and what is pi max? We don't know, but we can find upper bound for pi max, and this upper bound will depend on the dynamics. So using the Cauchy-Schwarz, usual Cauchy-Schwarz inequality, combining the Chebyshev inequality, we find this bound for open system, closed system. So delta t is greater than this quantity, which can be interpreted as a quantum speed limit, which is a different thing. I don't have time to explain what it is. You can ask me questions after. But basically, I can relate the two, quantum speed limit and the distribution. And for the closed system, we find that the product of the standard deviation for the time and the Hamiltonian is bounded below by h bar divided by 6 per root 3, best I could do, times delta theta, where delta theta is the population transfer between the initial state and the target state. Okay, so we find, and that's to some extent, it is a real time uncertainty principle in the sense like time is, in that case, delta t is not a quantum speed limit, but this is a standard deviation of the probability distribution. So for the Hadamard dephasing model, we found this lower bound, which is consistent with the physics because gamma increases, the dephasing rate increases, then you expect the bound to decrease as well, okay? Because it becomes more classical. So what do we have here? First, that's the end of the first. So we have a time of flow distribution, so a concept from which we can determine the temporal profile of a transition through projective measurement. I think we could extend it easily to a POV. Avoid the Zeno inhibition because we don't do continuous or repeated measurement. We have two alternative protocols, indirect protocol and direct protocol with the current operator. We can find, calculate and measure the mean transition time, the uncertainty. We have also a new context dependent because it depends on the operator, of the measurement operator here. And okay, but we could actually find the same bound in both. Okay, so time uncertainty principle. It works for both unitary and local system, and the value for discrete and continuous system. So okay, so everything I promise is done. An application now. The time of arrival. So okay, so now we want to find a way to define the time of arrival problem using this concept. How do we do? We find a projector that will be suitable for it. And the good projector, I believe, is the projector onto the half space. So imagine, okay, here is my atom. I drop it, and I want to see the time of arrival at this position x0. Okay. What I want is basically to measure, do a bunch of measurements, and measure the probability for the particle to be on the above x0. And then at some point, that's classically, okay? I will find 1, 1, 1, 1, 1, 1, 1, 1, 1, 0. Okay? And so, therefore, the time at which this atom will go through x0 will be the time at which the distribution will basically change, goes from 1 to 0. So if you calculate the derivative of that, the rate, that would be a delta distribution. So it's consistent classically. And now for quantum, I would just do the same exact thing. And the surprise is that when you calculate, actually it's not so surprising mathematically, but conceptually it was interesting to see that it works. that when you calculate the current operator using the formula I mentioned before, then we just find the current operator that we know for this type of system, okay, for a particle in space. That means that the time of arrival distribution is simply the normalized version of the absolute value of the current. And that's a formula that some Bohmian people found, except they don't have a protocol. And they use an ontology, so some metaphysical idea, based on the fact that trajectory exists, but how do you measure them? I don't know. Okay. Here I just have a protocol, you measure, you find it. But we cannot measure the current operator for this system, unfortunately, because the spectrum of X is continuous. Therefore, the current operator, there is no good way to measure the current operator through a direct measurement compared to the discrete case. So we have to use this indirect way to measure the. But there are systems, I found some system with some potential experimental realization that might work. Okay, so an application. So I talked about dropping an atom. There is a reason, because my question now is that, okay, can we use this protocol and find a simple answer to this simple question? A quantum race between two wave packets. So you have two masses, different masses, drop them, okay, use this protocol, protocol A, because protocol B, I don't think it's possible to do it. And then the question is, which one will arrive the first? The massive particle, the less massive particle, or both at the same time? We know classically that both arrive at the same time. Okay, no problem. Well, it is for quantum physics. Intuitively, I will say that the reason why I work on that is because I was thinking, okay, the less massive particle has a double wavelength that is larger. So there's more quantum fluctuation. So that means the particle can go either up or down because of the quantum fluctuation. But if you calculate, this is a problem for high school, if you calculate the average time of arrival for a particle that goes down with a velocity 1 meter per second, or up with the same speed, so 1 meter per second, you calculate the average time of arrival, you will not find the classical time of arrival corresponding to a particle that you drop, you will find something greater. Therefore, I expect, based on this intuition, that the less massive particle will arrive after, because of this quantum fluctuation. Is it true? I don't know. We'll see. First, a little bit of heavy math. Heavy. It's not very difficult, but we see. Anyway, so we can find, just to mention, using the time of flow distribution, we can find a simple expression for the distribution. And that works for any Gaussian state, any Gaussian state. That's the formula. So as far as I know, I've never seen this formula in the literature. Okay, now, but this is really annoying to calculate the average time with this distribution. So we use a trick, and the trick is to introduce this truncated normal distribution. Why truncated? Because t has to be greater than 0, therefore the distribution psi has to be less than a certain value. And I can relate this time random variable, time of arrival, position x with, I use x with this psi, okay, distribution. And then I get another alternative representation, which is a more stochastic representation of the stochastic variable t, based on this relation. And by the way, using the method of transformation that we often use in probability theory, we can find that psi actually is, it's a theorem actually, is a truncated normal distribution. So I just introduced this relation, so that's my definition of psi. I found that it's truncated normal distribution. So you may say, this is not really simpler, this is not really simpler than that. Actually, it is because we have a bunch of parameters that we Q, for example, I will tell you what it is. And then we can do some Taylor series, and this is better to analyze the time distribution, the time of arrival at different regimes. So let me introduce the physical constants. So TC is the classical time law. Q is a unitless factor, so it's what I call the quantumness factor, which is the double wavelength divided by sigma. Sigma is the width of the wave packet, initial width of the wave packet. And beta is the far/near field regime parameter, which is roughly, forget the Q, it's roughly sigma divided by x. So this is if x is very large compared to the width of the wave packet, it's of course far field. If this is close or even less, this is near field. Okay. So they are the two parameters that are important. Physical parameters that are important. Physical, unitless, but characterize the physics. And if you look at this formula again, then all these parameters appear. So now we can do, depending on the regime where you work, you could do Taylor series and find this formula. So these formulas, what are they? The mean time of arrival. Okay, I calculate the mean time of arrival, sorry. That's the relative difference with the classical time. So T4 is the quantum time of arrival. And you find a nice and neat formula. So the relative difference is proportional to Q squared divided by 2 in the semi-classical regime. So when both beta and Q are very, very small compared to 1. And in the far field still, the quantum regime when Q is very large, you find this formula. And that depends on Q. So this is proportional to H bar. Here it's proportional to H bar square. H bar square. So you say, well, this is very small. Yes, but if you work with very light atoms, very narrow wave packets, and lower gravity, and you can do it even in space. Personally, I don't want to, but or you could do it in a drop tower in Germany. There is a drop tower, so they drop the tower and then they work in lower gravity. Then you should be able to find actually to be in the quantum regime. But with some atoms on Earth, you could find if sigma is of the order of 10⁻⁷ meters, which is typical in experimental regime. The mass is about the mass of the hydrogen atom, and X is small enough, then you can find that of the order of a couple millimeters. But it has never been done experimentally because it's a little bit technical, I would say, experimentally. And also because there were no reason before to look at this regime, because there were no predictions of such an effect. Okay? But now, when I talk a couple of times to experimentalists, and they say, wow, okay, maybe that's worth looking at it. So this is what I try to do now, okay? By the way, notice that I was right. If the mass decreases, then delta increases. So the lower mass will be the slowest mass, okay? And for near field regime, well, that's actually experimentally, I can't really think about it, but then this is very huge actually, delta factors. Okay, so that's just a curve to, so that's, the red curve is the actual value and asymptotes are given there. The blue line, blue dash is basically the semi-classical far field. And the green is the semi-classical quantum. No, so the opposite, quantum far field. Okay, so it works. Okay. And that's the here is the near field, here is the far. Okay. Well, now time uncertainty. What about the time uncertainty? Okay, we're using the bound that I showed you earlier, so using Chebyshev and Cauchy-Schwarz, we can find the same bound, but here we calculate the variance with respect to the state. So this is even better. And we found that, okay, so that gives you a good insight about what is the minimum sensitivity of your detector in order to have a good resolution of the time distribution. So that could be useful. But what I realized is that, wait a minute, if I multiply delta x, so the standard deviation of the position by the standard deviation of the time of arrival, if sigma is greater than a certain value that is pretty small, then you find this bound, this lower bound, which is h bar divided by 2mg times a factor. So I investigated further, and I found that in the far field regime, we have this bar, okay, so delta T is greater than h bar over 2 mg sigma. So if you multiply by sigma, you find exactly even the sharper bar. That's the sharp bar. So that means that you cannot measure the initial position very precisely, both at with the same experimental condition, and the time of arrival at the same with this very large precision. You have to choose either this one is precise, the width of the wave packet, or the time of arrival, but not both at the same time. When I say time, you see what I mean. That means the time of, in the sense of with the same experiment. So in the near field regime, it's even more important, this value. So that means that that's the question that is general. I mean, I'm convinced it works numerically. I did it in 4 different regimes, but I have to find a proof. That's my future goal. That delta T, delta X is actually greater than constant, universal constant. Universal constant in the sense that does not depend on X or sigma, multiplied by h bar divided by 2 mg, which is kind of beautiful. I like the h bar divided by 2 mg. I don't know, sounds good. And anyway, so, and that's the question is, so that, okay, so that's the numerical visual representation of what I said. And as you see, this is the lower bound that I was talking about. So it's above. Okay, so is there, like, can we interpret it as an Heisenberg relation between time and position? That's the question I'm wondering. Even though time in that case is viewed as a stochastic variable, so it's not an operator, so we don't have the same interpretation. But it looks similar. Is there an incompatibility between the time and the position when we measure time that way? Okay. Okay. So just to summarize the second part. So we have new results. So we think that there is a quantum delay. So the universality of free fall, therefore, is not valid in quantum physics. I didn't say the weak equivalence principle, because the mass is the same. The inertial mass and the gravitational mass are the same. I'm just talking about the time of arrival. This is a different thing. So time of arrival and so universality of free fall in that case, and weak equivalence principle in quantum physics, they are not the same point compared to classical physics. Just there are also new regimes that we identified. Semi-classical, the quantum, far field, near field. So now we can tell, inform the experimentalist, okay, look in this regime, you should see that, okay? And you should eventually find this quantum delay. So time, energy, uncertainty also gives you a minimum resolvable time difference, and that is set by the dynamics. And is there a measurement incompatibility between the time and time of arrival and position? That's another question. So there are other applications. I will need 3 hours to talk about everything. So what we did is that we can also generalize the time of arrival to any operators, not just the position, but the velocity, time of arrival at a given velocity, or any operator like the energy if the system is time dependent. It's generalized also for any Gaussian state. So what I'm looking at is time-dependent harmonic oscillator, which is an interesting problem for different reasons, like quantum thermodynamics, for example. We also did it for backflow. The time, we could find that there are some signature of the backflow in the time distribution. And you know, backflow has never been observed experimentally, really. So this is still a debate. How do you observe the backflow? Quantum backflow. And we did it also for quantum superpositions, where we see some kind of interference, of course. And Zitter-Bergen-like effect. Sorry, I cannot really say it. I work on that for a long time. I used this before, and I can never say it. I'm really sorry about that. I really practice, I swear. Okay. So current and future research. So that's the current research, of course. I would also like to generalize to open quantum systems, like for example the Caldera-Leggett model or some other model. The quantum gases. So I'm sorry. I wish I could have tell you something about that, but I'm still working on it. The question is what is the effect of the statistics, Bose or Fermi statistics, on the time of arrival, for example? And I know for sure there is an effect, but I cannot say more. Quantum tunning is also an interesting point, well time. And also everything for relativistic equation, because this time position thing, I would like to see if it's still valid in a relativistic theory. Okay, to finish, I would like to close this presentation with 3 quotes. So Henri Poincaré says, once in his last thought, this is the last book he was published after his death, the properties of time are only those of clocks, just as the properties of space are only those of measuring instruments. So I think this is still valid for quantum physics, okay? You have to look at what you measure first in order to talk about time and not talk about time in abstract metaphysical way. Pierre Duhem, which is a guy I really like as well to read, The Aim of the Structure of Physical Theory, published in 1906. The physical theory is not an explanation, it is a representation, back to the debate we had yesterday. And the great Heisenberg, of course, in 1958, he published a book that I really like reading, Physics and Philosophy. I encourage you to read it if you have not done yet. What we observe is not nature itself, but nature exposed to a method of questioning. And I like to call this the epistemological mirror. Epistemology in the sense of knowledge. So when you look at nature, it reflects who you are. So in some way, when we question what is time, the good question is what do we want time to be? Okay, that's papers, and that's other papers, more about the philosophy, actually, physics. And I thank you for your attention.
Well, I'm not searching because I'm too old. Maybe some people will be interested in searching new. So, actually, my first visit to this institute, I'm very thankful for invitation. It was almost 20 years ago. At that time, I was cooperating with one of the founders of this quantum mathematics, quantum algebras, Peter Kulish. If somebody remembers him, he passed away, unfortunately, a long time ago. But we came here because his student got a position, a kind of postdoc with Tony. I don't know whether anybody except of Tony remembers him, Maxim Samsonov, but he was actually a talented guy. So I believe he quit both mathematics and physics and so on, but we came to cooperate. And then after that, somehow, maybe shortly after, I came to very nice joke, suggestion to start a project which I called QQQ, which is, this is quantum algebras. This was quantum integrable models, and then quantum information.
There was a conference on QQQ in Estonia, right?
Yes.
I attended it.
This unfortunately, this Estonian conference where I'm big time spent now, very dangerous place in the world at the moment, unfortunately. Could be even more dangerous because of today's political events. Could be even more dangerous, but anyway, it was 2000. It was a kind of culmination of this project. So you were there, Tony was there, so, and also very famous guys who passed away, Yuri Manin, if you remember him. It was in Bonn. He was director for Max Planck für Mathematik in Bonn, and it was celebration in August, not celebration. In his memory, big conference, several Fields Prize winners came to this conference. It was also Ludwig Fadeev, if somebody remembers him. Ludwig Fadeev attended this conference also. So, but it was big. So my part is here, quantum algebras, and then quantum integrable models, it's, I would say, to me it was schoolish. The main name in quantum information was Tony and some other part. But unfortunately, you see that this part is quite far away from this part. So I'm sorry for this, because it looks like this conference is mainly quantum information. But I will mainly, but well, this is my impression. I'm sorry very much, but I will touch a little bit integrable models because. So let me start with a story which I personally know. The history of quantum algebra started, roughly speaking, 50 years ago, when the school in Leningrad, led by Ludwig Faddeev, what I know from, so I know all these people personally. Unfortunately, only one of them, I believe, is doing in quantum information is Korepin. The rest, Ludwig Faddeev, so Piotr Kulish was mainly in quantum integrable models, Takhtajan, probably also Leon Takhtajan. Sklyanin, he is in England, he is a member of.
He visited here once.
Yeah, he is nearby. Evgen Sklyanin, Reshetikhin, if you know, he moved from California to China recently, working under Yao. Yao also, famous Yao, also moved from States to China, so Reshetikhin followed him. So probably know Korepin is still in States. Semyonov, he was in France, but I believe he retired now. Semyonov Tianshansky. So this is whom I know, all of them personally, and related work by the Japanese school. Jimbo, Niwa, and okay. Then the next period, I would say about Greenfield. So what he did, Greenfield. So hopefully some of them heard this name, Vladimir Greenfield. Nowadays also retired from the University of Chicago. In American scale, very young, so he retired being 71. In States, it's almost impossible, but he explained to me the reason why he decided to retire. So he joined this group somehow, some Leningrad group. And what he did during this period, he defined some classical analogs. In St. Petersburg, in Leningrad, they invented famous, I don't know how famous it is now, the so-called quantum Young-Baxter equation, which is behind, just a question, should I write down what it means? Or everybody knows?
I don't.
You don't know? Okay. So roughly speaking, if A is an associative algebra, unital, associative, blah, 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 with the properties, and we have some tensor in A, then R12 is R tensor 1, and this is A tensor Q. Similarly, you define R23, which is 1 tensor R. And somehow you define R13. And since the tensor product of associative algebras is again associative algebra, the equation looks like this. R12, R13, R23 equals R23, R1. Somehow this equation is behind integrability of many quantum integrable models, these equations. Particular solutions provide integrability of certain integrable models. And this was discovery of this Leningrad school. Then actually,
Well, so Baxter had the star triangle.
yes, but it was a kind of not explicit, no. Something like just a tool, not a, more than that, one of the first books about Yang-Baxter equation and quantum groups, they say that the quantum Yang-Baxter equation was known to specialists in how to say it, something like 100 years ago, as usually. Yeah, but it was known under other name. But really, you're right, it's due to Baxter, but they derived this equation, found its meaning, and so on. And already Sklyanin, British, no, English, professor, what he did, he assumed that there is expansion Rs and then he derived the equation for the small r, which turned out to be, he derived the so-called classical Yang-Baxter equation, which I will mention later. What's the difference? It turned out, as usually, that if one wants to classify solutions of the quantum Yang-Baxter equation, I doubt whether it works mathematically. Doubt very much. While solutions of the classical Yang-Baxter equation, there are tools to classify. A lot of mathematical tools, and my talk will be in fact devoted methods to classify solutions. Then, of course, there is another important question. If you have the small r, is it possible to construct big R? The question was solved positively. It's called Greenfield problem. It was solved by Ettinghoff. Ettinghoff, he is from MIT, was last year editor-in-chief of the Journal of American Mathematical Society, which is the one of two main journals in mathematics, Annals of Mathematics in Princeton, Journal of American Mathematical Society. Ettinghoff and Kashdan, who was a long time ago professor of Harvard, but moved to Israel.
So may I ask, is this the same Baxter, the combinatorial guy who solved the
I believe.
classical model?
Yes. So Baxter, in solution in his model, somehow implicitly introduced these R matrices as a tool. But development of this, not development, I mean, applications of these R matrices is due to some Leningrad school. They invented how to deal with it. So Sklyanin invented, Evgeny Sklyanin, but I don't know, he's not from London, but from England. He introduced the classical Yang-Baxter equation, and then in '82, Greenfield, together with one physicist, Belavin, they classified solutions of the classical Yang-Baxter equation in some way, because there are different versions. So, and then after that, continuing to work with classical Yang-Baxter equation, Greenfield invented the main algebraic tools in solutions of the classical Yang-Baxter equation. They're called Levi algebras. Then Manin triples, which is some related notion. Greenfield classical and quantum doubles and Poisson homogeneous spaces. So he invented a lot of classical tools which are useful to solve the classical Yang-Baxter equation. So probably if I have time, some will be defined in my talk, if not. So, but notions are not easy, notions, and interesting enough, they were more or less completely unknown before Greenfield. Something like Lie bialgebra. So Lie algebra, you know what it is, but Lie bialgebras turned out to be a completely new notion in mathematics. Okay, we'll talk about maybe later. Now, what happened? So Greenfield was working in this area of mathematics, roughly speaking, between 80 and 90. And at the end of his quantum algebra career, he invented quasi-Hopf algebras and their limits, quasi-Lie bialgebras and Manin, not triples, but Manin pairs. Okay, probably no one of you heard about Manin pairs, no? So let me define this notion, which is important. The notion is as follows. If we have an inclusion of two Lie algebras, L and M, and on M we have not the famous Killing form, but this type of form, which is invariant, symmetric, non-degenerate, and so on, which has exactly the same properties as the famous Killing form, but not necessarily Killing form. It happens. So there is a form here, and then with respect to this form, L coincides with its orthogonal complement with this form, which is called Lagrangian. And this pair is behind of quasi-Hopf algebras, but maybe I will, if I have time, I will tell you what it is. Okay, and then what happened? Around 94 yesterday, we discussed with some people. That time Fields Prize winner Zilmanov, and he was working in completely different areas, suddenly came out with a nice idea. And I remember that, say, in mid-90s, people working in this area, say, at least Russian-speaking people, all of them said Greenfield knew everything. But this was certainly a fact that Greenfield didn't hear. And what was this fact? And I'll explain to you the value of this fact, which is based in classification theories. So, since it's very important, I will write it down on the board. So assume we have a Lie algebra graded by root system. A typical example is, say, SL2 with coefficients which is the same as SL2C tensor product with polynomials. Here. So this algebra is of this type. And assume we have here a Lie bialgebra structure. So what is a Lie bialgebra structure? Since I was not ready, so I need to say two words. So we start with Hopf algebras. The main feature of Hopf algebras is we have the so-called famous co-multiplication, and algebra map from H to H tensor H, because if H is associative, H tensor H is associative. So this is a homomorphism of algebras, but this is so-called co-associative. So there are two ways to go to H tensor H tensor H. So here delta tensor identity, and here identity tensor delta. And these two ways should coincide. There are other axioms, but let us stay with this main axiom, co-associative. And of course, one, because you know there are many relations between associative algebras and Lie algebras, so one wants to have something similar for Lie algebras. But the problem, of course, is that the tensor product of Lie algebras is not a Lie algebra. So this is the main obstacle, while Hopf algebras came out from topology 100 years ago or so. There are several Hopf German mathematicians, and there is Wiener Hopf integral. Yes, does it exist?
Yes, it does.
But I believe that it's a different Hopf. Not the guy who invented Hopf algebras. No matter. But so you need to modify definition, and somehow, in spite usually development of mathematics, you develop some classical stuff and then try to find some quantum. This is a different way. These Hopf algebras, they relate to quantum things, and Lie algebras to classical things. But Reinfeldt came out with some definition of this. Is called co-bracket. Maybe I don't need, so axioms are a little bit more complicated, not so easy to say like this, but together with this map, we say that L is a Lie bialgebra. So it has a Lie algebra structure and some the so-called co-bracket, which satisfies certain axioms. But the main feature is that the dual map delta star provides a Lie algebra structure on the dual space. So this is how it works. And even we are not there. What is more important that there are two doubles which are important in my talk. We start with the quantum double. Axioms of Hopf algebra, of a Hopf algebra, constructed in such a way that the dual space H star also becomes a Hopf algebra. And the double, quantum double, this is the vector space is H star tensor H is a vector space. Then H star is an algebra, so we can multiply two elements from H star. We can multiply two elements of H. But the problem is that there is extremely non-trivial way. So roughly speaking, any element of this, they have form A equals H star times H. And since we deal with non-commutative algebras, the order is the order matters. So the question is, there is a highly non-trivial way which Drinfeld invented, how to multiply in this direction, H times H star. And if you heard not so much about Hopf algebras, it's really a challenging thing how to multiply H times H star. So you need to switch it back somehow.
No, I don't understand.
So
H star, is it H star or?
yeah, of course. H star is an H star and H in H. And when we write like this, elements here is a product, star element from here times, well, combination.
But then what is H star? Because that's not.
It's an algebra. It should become an algebra, double. So you need to can multiply in other direction. So if you have a linear function, say you can multiply it by definition, it's just product. So any product, any element here, it has this form. On the first position is H star, on the second position is H. Now you want to make algebra out of it. In algebra, you need to multiply also first H, but then H star.
So, but they're in different spaces. So
No. It's one and the same space. H star tensor H. They're the same vector space. This is just a vector space. And we want to define an algebra structure in this vector space. So if we have two elements from this part, we multiply as they are. If we have, so we also can multiply such two elements. Then this element is defined by definition in this order. So elements of this space are by definition of this form. First you have some term from H star and then from H. Any generic element is a combination, linear combination of such things. But now you need to be able to multiply them in the opposite order. And this is highly non-trivial. I don't know what to say more. But first question, is it clear that any element from this vector space can be written in this form? H star just by definition. You have a tensor product of two. You have first component, second component. So this is Uri, this is here, and this is here. Any element, well, if you wish, you can write it. But then it's better to omit this tensor sign. Just by definition, this. Tensor product of two vector spaces. I cannot say no.
Just a naive question.
So,
A naive question on some which are,
I'm sorry.
one could make sums.
Yeah, of course. But of course, I thought for physicists, it's, of course, it's formal sums, HI. Okay. Formal sums, but for multiplication, we need only, this simple terms. But now we want to define, so we have these guys. They form a basis by definition, but then we need to be able to multiply in opposite direction. And this is a highly non-trivial problem which I don't want to discuss. but there is a solution. Well, unfortunately, it's the essence of quantum algebras. So I don't understand.
Well, H is not in H star, so you can't write it like that.
But I want to define a multiplication on this vector
Yes,
space.
you have to multiply two elements of the form like A that you've written there.
Okay. Unfortunately, then I need to use something. We want to multiply so this is one element and this is the second. But in order to multiply, it's an associative algebra. You need to switch an order in this product in the middle. And this is what I try to say. You need to switch this somehow to write it that this is B1 star. You need to be able to write in this way.
Is it the same product?
So
I'm confused about the type of product between HR star and then HR. This is a tensor product. But what you say is that you would like to write H star using a dot product.
it's just by definition, all the elements of this vector space, their combination sums
Just wrote that.
E, I, E, J.
Tensor.
But better to
Yeah. But
better to take it away.
the product between A star A and B star B is a dot product? Or is because you put a
You need to define this product.
yeah, okay.
You
So
need to
want
define
build,
this product.
okay.
But
Structure
you need
operation.
to express, so this is a basic element, this is basic element, and you need to express this product as a linear combination of basic elements. But basic elements are of a different form, not A, B star. So we need somehow to switch products. And this is, in Hopf algebras, what Drinfeld invented, how to switch this product, which is highly non-trivial. So if you don't know this stuff, it's really non-trivial stuff. But
Is there then a formula?
it's there is no I cannot provide formula, it's too complicated. So, but there is a formula which says that A times B star
Can be written.
can be written like this. There is a complicated formula which involves co-multiplication, antipode. I haven't mentioned antipode in Hopf algebras. So it involves this formula antipodes, co-multiplication taken twice and so on. So of course there are in these modern theories explanations why it is so, but in formulas it's quite non-trivial. So there is a non-trivial formula which said that this is possible, and which this formula converts this into an associative algebra, which is called quantum Drinfeld algebra.
Is that also a Hopf algebra?
So it's also Hopf algebra, but let's forget it for a moment. It's easy, but it's also a Hopf algebra. So this is the so-called quantum Drinfeld double. And what about classical double, which is also a non-trivial problem? So we know what is the quantum double, and now the classical double. Of course, it's usually tensor product should be substituted by direct sum. But it's not a direct sum of two ideals. Again, we have the same problem. We know how commutator of this here, how it looks like. It's just an L. L star also is a Lie algebra, also we know commutator. But a non-trivial problem is to find the commutator element L with L star. Now the order does not matter, the order, but we need to find the formula for this sum. In order that this double remains Lie algebra. So it's, I would say, I cannot say that the algebraic problems of extreme difficulties, but it was never invented. So Hopf algebras were known since 100 years ago, Lie algebras 150 years ago, but no one invented this stuff until quantum algebra time, these formulas. And since we don't need explicit formulas, actually, this I will not. Okay? So it's possible. And not extremely obvious. So it's not obvious. Now, what was thing which an outside guy to this science, Zelmanov, invented? He invented the following fact. Assume we have, say, G of U, so polynomial, formal polynomials with coefficients in a simple, now it's very important that this is simple, the algebra U, and we have some Lie bialgebra structure on this G of U. Then we produce double. And this is what I say, the G tensor C polynomial U. Then it is obligatory, has form. This is a complicated theorem. This has a form G tensor B, where B is a commutative, associative, unital algebra extension of A. And this moment provides a tool how Lie bialgebra structures or equivalently somehow solutions of the classical Young-Baxter equation can be classified. An example of this is here. So this case relates to Dublin Institute of Advanced Studies, this case, because this theory was invented here during my visit in 2008. What Zelmanov did, he sent me here his notes. It was not published at that time. He sent me notes saying the following fact, that if you have this, instead of polynomials, formal power series, then we have some trivial option for B, one trivial option, and just 3 non-trivial options. Laurent power series, option number 1. I'm sorry, that's better to say C of U plus 1 copy of C, and C Laurent series we have just 3 options. C of epsilon, epsilon squared. And it gives us so it will give us tool to classify Lie algebra structures. But after we classify Lie algebra structures, surprisingly, we will see that something happens. That there were at that time known quantum algebras, but it turned out that the list of quantum algebras is not complete absolutely. So classical situation, since any Lie algebra can be risen to quantum group, to quantum algebra. So it will mean if we find new Lie algebras, we will find something, it indicates that there are new yet unknown quantum groups. This is the logic behind this. In my talk, quantization of classical algebra, such as Lie algebra, quasi-Lie algebra, Lie algebra. People don't know what it is. I will tell you what is a Lie algebra, and Poisson homogeneous space. What is known about these quantizations? If we have a Lie algebra and we quantize it, we get quantum group, what is called quantum group, which is a Hopf algebra. If we quantize quasi-Lie algebras, we get quasi-Hopf algebra, which is, if I have time, I will say a couple of words about quasi-Hopf algebras. Lie algebras, we will discuss a particular case, but I talked to Reshetikhin and he said that a big problem in this area that there are no quantum counterparts of classical Lie algebras. So I will try to say, to my opinion, what it is, at least in particular cases. And then Poisson homogeneous spaces, probably I will not be able to define. Let's see how much time. Oh, almost. Okay, sorry. It's conjecture that we will get Hopf module algebra, but we will concentrate on first and third. In 2008, Tony Dorlas invited me and Piotr Kulish here to work with, at that time, Tony's postdoc Maxim Samsonov. In Dublin, I received a package from Zilmanov, which contained his unpublished notes about Lie algebras. However, one of the most known quantum groups is called Yangian. Probably, I don't know, hopefully some people of you heard about Yangians. No? So it's an extremely complicated Hopf algebra, which is a quantization of not formal power series, but polynomial algebra. So relations are extremely complicated. It's completely unclear how Greenfield found relations, algebraic and co-algebraic relations. But this group, if you check internet, It appears everywhere in combinatorics, in representation theory. So this is, I would say, mostly widely known quantum group, which is called Young. Of course, the name is Young, who, you know, he passed away in October, young, and age was 103 years. And he also, he is a Nobel Prize winner in physics. And he was working at the University Stony Brook, Long Island, but also moved to China. Everybody moves to China. Tikhin moved to China, Zelmanov moved to China, Young moved to China, and Yao moved to China. So, but it says something. So China invests, unfortunately, more money than European countries, US in this science. And people say, okay, we want to do something. So already in Dublin, all the Lie algebra structures on polynomial were found. And the most interesting Lie algebra structure on polynomial is given by the following classical R matrix. So I will write down classical R matrix later. What it means. But why it is called Youngian? So almost usually Lie algebra structures are given by solutions of the classical Young-Box equation, almost always. And I'm so bad losing. So if we have G of U, then delta is given by and this is the simplest solution of the classical Young-Box equation. Omega is
You better write the classical Young-Box equation.
it will appear. It will appear. So this is the so-called Casimir element. And so this is the simplest solution. In physics, frequently, like a permutation matrix, which switches between components in a vector space. So, and its quantization, Young. The quantization of this situation is called Young. But I found that here in Dublin, almost 20 years ago, immediately with a bit of help of Maxim Samsonov, I found that actually general solution should be substituted. It looks like this. If we have in SL2 the standard basis E, F, and H, the standard basis of E, hopefully. So E is consequently F, if we have the standard basis E, F, H. So it's not like sigma plus sigma minus, it's E, F, and H. Then we have this formula in SL2, general formula. And what is known about quantizations? If these constants P and Q are zero, then it's Youngian, which was known. If P is 1 and Q is 0, it turned out that this is almost unknown quantum group, which my another co-author Tolstoy called Drinfielddian. So how it looks computations in this quantum area? I had some solution of the classical Yang-Baxter equation for 2x2 matrices. And then Tolstoy got interested, his background is physics, to produce the corresponding solution of the quantum Yang-Baxter equation. So how it worked in 1998, approximately. He made some conjecture that this quantum R matrix should look like. Then he computed this left-hand side R12, R13, R23, and right-hand side. He received 800 terms on the left and 800 terms on the right. Some of them crossed out, some of them left. So then he adjusted his conjecture, and after 2 years of such work and 2 such notebooks, he came out with a formula which consisted of 3 terms. But altogether it took 2 years, and so hopefully maybe AI will help to reduce this problem now, but 30 years ago it took 2 years of job, and then I don't get it was maybe not 800, maybe 780 terms on the left and the same number of terms on the right. Some of them canceled out. And then he got even more interested in this stuff and invented Drinfielddian. Okay, if we deal with other P and Q, nothing is known. So, and it's a basic solution. So even nothing is known for SL2, and of course nothing is known for other classical algebras like SLN, orthogonal, simulated, exceptions, nothing is known. So it's a way to look for, but of course, because of theories, there should be a quantum group which quantizes this stuff. Okay, now let me pass to even less unknown stuff, Lie algebras. And it was invented again in St. Petersburg in Leningrad school by Semyonov-Tenshansky. Who ever heard of him? He was working in France for a long time. You know Semyonov-Tenshansky, no?
Well, I know.
Yeah, well, he is from some merited family, Tenshansky. His great-grandfather, so he was a famous explorer of Middle Asia, of Tian Mountains. That's why he received from the Russian Tsar double name Semyonov, became Semyonov-Tenshansky. So he inherited his name. So he invented the so-called, what he called later, Lie algebras. So let L be a Lie algebra, following Semyonov-Tenshansky, let us introduce the second structure. We take some R, just a linear map, such that this type of bracket also provides another, the second Lie algebra structure. And surprisingly, it's not so difficult to find such an R, which produces the second structure. And the main example is as follows. If L is a direct sum of 2 subalgebras, not ideal, then the difference between them provides a Lie algebra structure. Why it is important? Let me try to main example is that if we have L, this is formal Laurent series, and then we try to split it into parts. One is formal power series, Taylor power series, and the second part is whatsoever, any list of algebra, And then we have this formula for R. But now let us notice that there is a invariant, symmetric, non-degenerate form on L, on this algebra. Namely, if we have two functions, then we consider their killing form, and then residue at 0. And then we get, in this way, from R, linear map, we can pass to tensor product. And now I write the classical Young-Buxton equation. If it appeared for this R matrix, this is the classical Young-Buxton equation. Using some standard procedure, we try to find, and then what we come out with some kind generalized. So observe that the difference is just in this form. This is R13, R23, and here R23, R13. So just changing indices, we get a new version. And surprisingly, what happens? If solutions of this version can be, say, classified, to describe all the solutions. Solutions to this equation, it's a wild field without any abstractions, it's really field. And now, so the simplest possible W is written for SL2. And following Semyonov-Tinshansky, this R matrix gives rise to generalized Godin model. In particular, we get this type of Hamiltonian, which should be a new one. So, but with this Hamiltonian, the system, because of it satisfies this generalized Young-Buxton equation, should be integrable mode. Does it play any role? I'm sorry, I don't know, I'm an expert, but it's a kind of what you get a bunch of new Hamiltonians which provide integrable modes. Hopefully some of them are important. And then my idea is how to get quantum quantization of this situation. So we need to take the double, which I explained. So Youngian is a Hopf algebra. We take its double. So its double also is a non-trivial computational problem, but it's doable. It's done by the same guy Tolstoy. He did double. And we need to present as a Youngian times some associative subalgebra. So this is my idea how to quantize the algebra. So if you remember, for Hopf algebras, it will be like this. D of the Youngian will be Youngian star tensor Young. But this Youngian star is a Hopf algebra. So my idea is that we probably can find not a Hopf subalgebra, but just a subalgebra. And the properties
if we factor out modular Planck constant h, we get the universal enveloping of this view. But the main question remains here. From here, one can produce big R quantum Young-Baxter equation. What equation can be produced in position? I don't have any idea. But this leader algebras is a tool to obtain new integrable models of Godin type. Do they play any role in theoretical physics or anywhere else? No idea. No, I'm sorry for this. Probably it's exactly time to stop.
Thank you very much. Already some questions.
No, it's not questions. Let me finish. So trying to thank you. And dear Tony, I wish you a long, successful, and healthy life.
Okay. Maybe we have time for one more question and then we'll straight to the second speaker. I have a question.
Yeah.
The solutions of the Young-Baxter equations, the R's which you wrote down, the solutions are certainly not unique because I can
Yes, it's a list of them.
So yes, and so can you say anything about the structure of the solution space in terms of the A?
In terms of what? A? What?
Yeah, you had.
What do you mean A?
No, you wrote down
Quantum or classical? Quantum. The only thing I can say that they start 1 tensor 1 plus H, this classical R matrix, which I know, but then how to extend it further to get solution. This is what I said. By hands, it takes 2 years.
Okay.
In the simplest case, absolutely simplest case, it takes 2 years. And...
Okay. On that positive note, let's thank you very much.
So I'm very happy to be here. I have fond memories of collaboration with Tony and Joe that's here on worked on Anderson localization in magnetic fields back then. Yes. And I looked up the dates of our papers. I think we published 4 papers together and some more with Joe. And this was before 2000. And the last paper is in 99. So it's amazing because yeah, time has passed. But yeah. And I would like to thank Shane and the Institute for organizing this workshop, which I enjoyed a lot. Okay, so when I got the proposal to come, I thought, okay, but what can I talk about? Because with Tony, we were working on quantum mechanics, basically. Quantum mechanics in magnetic fields. And now I'm working more into classical information theory, coding, inference, touching a bit of machine learning and so on. And I felt I really wanted to talk about something quantum. And I teach quantum information, so from time to time I'm thinking about various things. And I got aware of a conjecture that computer scientists like, that I would like to explain. And I thought, okay, I had some ideas and so on. So, 6 months ago, I started working on that. So that's because of you that I'm working on that now. I thought I have to really make progress. I have 6 months to make some progress. So it's work in progress, but I hope to convey something. Okay, so this will be about something related to circuit depth and global entanglement of approximate ground states. apart from the motivation of 2070, the other two motivations that one might have is the first one, this low energy trivial state conjecture that was formulated by Friedman and Hastings in 2013, is considered as an important stepping stone in computer science, in quantum computer science. It's a stepping stone to classify the complexity of quantum problems. But this conjecture has to do with concepts that have appeared in many body physics first, I think. And these concepts sometimes are called global or long-range entanglement and topological order, things that are not very well defined in the physics literature, but very interesting. And I think, in computer science, people try to define these things a bit more precisely. And one approach is through this conjecture here. Okay, so let me explain first what's the conjecture, the NLTS, so no low energy trivial states conjecture. So the conjecture says that one can construct some family of local Hamiltonians on n qubits, and by local Hamiltonian we mean a sum of elementary terms, m terms. M is of the same order as n, and each term acts only on a finite number of qubits with respect to n. We always think of n as tending to infinity or being very large. Moreover, each term has to be positive semi-definite. And the idea is to construct such a family of local Hamiltonians such that one can find a numerical small constant, so that if you take any state psi of low energy, that's the average energy of the state psi, not necessarily an eigenstate, any state in the Hilbert space that has energy less than the small constant times the number of qubits, then if you would attempt to construct the state psi as the output of a quantum circuit, and I will explain what this means, this quantum circuit could not have a depth, a finite depth. The depth would have to grow with n. Assuming that the input of the circuit is a product state. What do you mean with depth? So it will become clear. So, well, basically it's the number of layers, so that these circuits are constructed out of unitary 1 and 2 qubit gates, okay? And time goes from left to right. And you have a certain number of layers in the circuit. So somehow is the size along time of the circuit. I'll show pictures to be clear on pictures. Okay, so this was a conjecture, but there has been progress recently. So people have indeed provided constructions of such Hamiltonians based on the so-called Algebras in short quantum error correcting codes. Well, for this talk, we don't have to care about this. And then there was more recently another construction based on combinatorial, the combinatorial K-sub problem, which is a constraint satisfaction problem that is very important in computer science. We also don't have to care about it. Here, I will provide a much simpler construction, which is more connected to traditional statistical mechanics. In fact, the construction is only based on the Ising model. So somehow the Ising model will replace the error correcting codes of the KSAT problem. The idea of the proof of the conjecture is, well, maybe philosophically is the same, but it's somewhat different, I think, and it's more elementary. But immediately a disclaimer, what I will show is a somewhat weaker form of the conjecture, although you'll see in the conclusions that the way it's proved in these papers, there are still unsatisfactory issues. So I think it's not the end of the story. Okay, so before I turn to the construction of the Hamiltonians, I would like to talk a bit about this notion of global entanglement that was in the title and is not directly formulated in the. I mean, it's not obvious. But first of all, I would like to say what I mean by that. And also, it's not obvious that the conjecture has something to do with global entanglement that I hope I'll convince you. So for the moment, no Hamiltonians. I just want to talk about properties of some states. Okay. So let me take n qubits, and let me take these two GHZ states. So I have a tensor product of n qubits in state 0 plus tensor product of the qubits in state 1, or I can do the minus superposition. So these two states of n qubits are orthogonal. So they are perfectly distinguishable because they are orthogonal. So essentially, if you have only these two states in the world, this is like a classical world. And this relates to one of the talks yesterday. However, if you compute the reduced density matrix of these states for any subset of the qubits A, so the rho A plus and rho A minus associated to the two states, you find this very simple density matrix, diagonal density matrix. 0A means all the zeros in the subset A. 1A is all the ones in the subset A. So that's a very simple convex superposition of two trivial projectors here.
What does the sign mean? Two angles, second zero, this one, and 0A with the brackets here, the next term. Yeah, that one. No. 0A.
Oh. So that's a bar. So it should be a straight line. I'm sorry. Okay.
Yeah.
So
I understand.
Get the bar.
Yeah.
Yes. Yeah. I'm sorry. It's a straight line. Yes. Okay. So what's important here is that these density matrices are the same for the plus and the minus state, and also essentially they don't depend much on the set. They depend on the set. Somehow they are trivial. So what this says is that locally, if you look at the system, if you take observables that are supported in the subset A, you cannot distinguish the two states. If you would do measurements only in the subset A, the average of an observable, we compute it with trace of rho plus times the observable, or trace of rho minus times the observable, we find the same thing. So even though the states are globally different and completely distinguishable, locally they are not distinguishable. Okay, that's very peculiar. And this can be.
Can you take the A, the whole set from all to the end?
Not one.
So
No,
I have to don't understand the statement then.
Okay, I'm sorry. It's a strict inclusion.
Subset.
Maybe a strict subset, yes. Yes, nice. Okay, so people sometimes use this, can use this observation to define what's called global entanglement, or sometimes people use the wording long-range entanglement, although there is no notion of distance for the moment. Okay, so a state is globally entangled if you can find an orthogonal partner which is perfectly distinguishable, but however these two partners are not locally distinguishable. Okay, this is what I mean by global entanglement. Okay, now the question that I want to address is when you have a globally entangled state like that, and you want to construct it as the output of a quantum circuit, how long should be this quantum circuit? Because if the entanglement is somehow global, maybe you need a long quantum circuit so that this entanglement has time to develop. Okay. So what is a quantum circuit? I have the lines here with inputs that by convention I set to 0, or this could be other single qubit states, but let's set them to 0. So in the input I have a product state, and this Hadamard matrix prepares superposition of 0 and 1. And then by putting a staircase of these are called control not gates. So if this bit is 0, then you do nothing here. If this bit is 1, then you flip the bit down here. So in any case, with such a circuit, the output is going to be the GHZ plus. And if you want the minus, you can start with the state 1. Okay, so with this circuit, the depth of the circuit is n. So this is what I mean by depth, is the number of layers when time flows from left to right. So I apply one unitary here, then the second one, the third one, the fourth one, the fifth one. And I have to apply them in a sequence. Okay, so the depth is the number of layers. Each U1, U2, up to UD is a layer in the circuit. Okay, now I can do better than this construction and somehow compress the circuit. So for example, I can, instead of putting the control not here, I can use this qubit as to control the third one. So these ones I have to apply one to the other. But then these two control nodes, if I replace them by this one here and this one here, these two here, you see, I can do them in parallel, because this one I can push it in parallel. I can do it like here. So this whole thing can be done in one time step, basically. Okay, so I can compress the circuit. Yes.
For this notion of global entanglement, is the size of the subsystem important? Like, could it be that the reduced density matrix on a single qubit is indistinguishable, or does it have to be some kind of minimum size of the subsystem?
So in principle, we would like that all density matrices on all subsystems don't allow to distinguish the state. Okay, so turns out that this has linear depth, but these kind of circuits, if you extend this construction to all n, you can see that they have logarithmic depths in them. Okay? So basically, these GHZ states can be constructed in logarithmic depths. Okay. However, if you assume that only nearest neighbor quantum meets somehow, if you are geometrically constrained, so for example, in the quantum devices that are fabricated nowadays, the qubits, they are geometrically constrained. So if this is space and you have a one-dimensional geometry here, the depth is linear. Okay, so it depends on your model of quantum computation, what's the depth. Okay, but in computer science, people don't care about geometry, and they like to model with depth log n. Okay, now, but could one do even better than log n after all? Okay, who knows? Okay, or can you prove that log n is the minimum depth that you can attain? Okay, so there is a very simple argument to prove that log n is the minimal depth, and this argument then you can apply it, to much more general states, and this is what I will do later on. Okay, so let me give you first the argument that says that if you're geometrically constrained, the depth cannot be smaller than basically order n. So let me take an architecture of a circuit where time flows from left to right. I enter with a tensor product state here. The output state is here. And this is called a brick wall architecture. So I allow only 2 qubit gates, say, or this could be also tensor products of 1 qubit gate and another qubit gate, or 1 qubit gate with the identity here. And the architecture is such that you can apply a 2 qubit gate here and here in parallel. Okay, so that's one layer of the circuit. And then, if you want to couple this qubit and this qubit, you have to apply this after. This one can be applied in parallel, and so on. So this is called a brick wall architecture, and you can construct quite general circuits. You don't take the same unitaries. What unitaries you take here is completely arbitrary. So here I have 6 layers, right? 1, 2, 3, 4, 5, and 6. Okay, so the depth here is 6. And now I introduced this concept of backward light cone, which is a completely standard concept. Let me take this output qubit J. The backward light cone is basically when I go back forwards in time, I look at the qubits that have interacted, that J has interacted with. So here, J has interacted with this qubit at this level, and this qubit interacts with Q5 at this level. So this here is the backward light cone of J. The backward light cone of I is the qubit I interacts with, and I interacted with this one, and this one interacted with Q4. So, and also this one interacted here with Q1. So this is the backward light cone of I. Now, these gates here are not, they never interacted. I mean, J and I don't interact with this part of the circuit. Okay, so you can decompose the circuit like that. And if you look at the output state and you take the reduced density matrix of the 2 qubits I and J, this means that you take the output state here. You take the density matrix of the output state. What is it? It's all the unitaries applied on the input. Here you have the unitaries applied on the input also, so this whole thing is the density matrix of the output. You trace over all qubits except I and J, so you trace over all these qubits. If you do the computation, because of cyclicity of trace, everything that's not coupled to I and J is given by this unitary blue one and blue one here. You can eliminate the blue one, so you can think of, for example, geometrically, take these three gates and just throw them away, further away, okay? So they go away. And then you see these two light codes, they don't overlap, so somehow the circuit is divided into two pieces. And if you do the algebra, you find that the density matrix eventually factorizes in a pure tensor product, a single tensor product of the density matrix of I alone and the density matrix of J alone. Okay? Now, if you increase the depth of the circuit here, so I increase the depth of the circuit, you see this green light cone here continues up to here, and the red light cone continues like that. So the green and red light cones, they intersect, okay? So if the circuit was deep enough, I mean, if it's deep enough, I and J, they interacted in the past, okay? And this is what will create entanglement between I and J. And if you do again, try to compute the density matrix of I and J, you will find that it cannot be factorized like that. It's not a single tensor product. It could be a sum of tensor products, okay? In fact, most of the time it would be a sum of tensor products. So these are called separable states, but certainly it's not a single tensor product.
It depends, of course, on the interaction. It could factorize, but only in very special
it could, yes, but in general, yeah, it could. Generically, yes, but yes. Okay. So you see that, in fact, you can show that if this does not factorize, then the depth for this brick wall architecture should be at least equal to the distance between the two qubits. That's the message. What I mean by distance is a sort of geometric distance. So you can think of this direction as space, and these qubits are really neighbors on the one-dimensional line. Make things simple. Okay, now if you don't want a brick wall architecture, you can also develop the same ideas. So for example, you see here I don't have a brick wall architecture because I can interact between this qubit and that one, so there is no notion here of distance. Anybody can interact with anybody. But then if you think about it, so I don't want to explain this figure, it is not very well done. And by the way, these figures are done with the help of ChatGPT, and at some point, that's why they are very nice, because of course, Joe and Tony, they know that I'm unable to do such figures. This back in 2000, I was unable. So, you know, even 25 years after, I'm still unable. So anyway, I lost patience, and I could not explain. I don't want a forward left one, I want a backward one, and then the lines are correct. Anyway, if you take an unconstrained architecture, you can again show the same thing, but because the architecture is unconstrained, the lemma becomes the following. If the density matrix Oj is not equal to a single tensor product, but then for any pair, you need this, because otherwise you could permute pairs here. then the depth will be at least log n. Okay. You have to think a little bit about it, but let's admit that. Okay, so now what about GHZ? If we take GHZ and we compute the density matrix of 2 qubits instead of a general set A, we find that it's this separable decomposition here. It's a convex combination of this and this density matrix, and the convex combination is non-trivial. So this does not factorize into a single term, but in a sum of 2 terms. Okay. So immediately this implies by the light cone argument that for GHZ, a brick wall architecture necessarily needs a linear depth, and an unconstrained architecture necessarily needs logarithmic depth. Okay, so that's the proof that you cannot do better than the example circuits I had at the beginning. So it's a quite easy proof, in fact. Okay, so this light cone argument is what I will use, and the computation of density matrices is that what I will use for the states that are ground states or low energy states of the quantum Hamiltonians that I want to construct. Okay, so I will give you an example of a quantum Hamiltonian that has a ground state and also approximate ground states for which the density matrix of any subset does not factorize into a single term. And then I have again a light cone argument. And then this proves that the state of the Hamiltonian needs a longer than log n or linearly. So that's the philosophy. Okay, how can I construct such Hamiltonians? Apparently, this was non-trivial for people. And indeed, I'll try to construct some Hamiltonians, not completely obvious a priori. So these quantum Hamiltonians have an underlying classical model that helps us to construct. So what are these underlying classical models? Okay, I'm not
sorry,
yet.
Nicolas, I'm a bit lost. So these Hamiltonians now replace the gates?
So these Hamiltonians, no, they don't replace the gates. These Hamiltonians have ground states, which I would like to construct through a circuit.
Okay.
Okay. Okay. So forget quantum mechanics for a moment. Let's come back to classical spin systems, if you wish. This group around Gamarnik used the so-called K-sat constraint satisfaction problem. I'll use an Ising type of model, but in general, all these models can be expressed like that. You have a set of spins, plus minus 1, n spins, and a set of m constraints. The constraints are depicted here by the little squares. The spins are depicted here by the circles. And these spins have to satisfy a set of constraints. So the constraints are local. It means that each function hc here is for constraint takes a finite set of spins. So h1 contains 2 spins, s1 is 2. So for example, here h contains spins s2 and s4, and you have to satisfy all these constraints at the same time. From the point of view of a Hamiltonian, your energy cost is the sum of the constraints, and I suppose that I pay only $1 if the constraint is not satisfied, 0 if it's satisfied. So these are binary valued constraints. Okay, so if you choose your so-called factor graph, and this can be a simple graph or a graph that's not embeddable in space, and so on. Then you get some sort of constraint satisfaction problem, and this is a very, very general class of CSPs or constraint problems. And the one we like the most is the Ising model and even the ferromagnet Ising model, so at the minus here. And this is a strange way to draw the square grid. I take the Ising model on a square grid. So what I mean by this picture is that the spins, they are on the circles, and the constraints are the little squares here. That is another name for an edge or a ferromagnetic surface. So every time you have a square, you have a ferromagnetic on the square. And I put this Ising model on a torus, so I wrap it around here and here. And this has only two ground states, two solutions, the all plus solution and the all minus solution. So it's the simplest possible constraint satisfaction problem. And this is what I will use. Okay, so now let's come to the quantum Hamiltonian. So I take this factor graph, the one of the Ising model, and instead of a spin on each circle, what I attach to the circle are four quantum spins or four quantum bits. Okay, so the red dots are quantum bits, and I define the GHZ state of all quadruple of quantum bits. So all quadruples of quantum bits, I will impose that they are in this state. Okay, this superposition state. And then for each ferromagnetic bond, if you wish, or constraint here, I define a projector that projects the quantum bit onto the subspace where the pairs here are both 0 or both 1. So that's a ferromagnetic projector. Okay, I need to invert this. Okay, so I need to regularize to get rid of the 0 eigenvalue. So I regularize with a small parameter gamma. I add gamma times the identity and 1 minus gamma times PC. So that's almost a projector if gamma is small, but this QC is now inverted. And my quantum Hamiltonian is the following. I take the projector onto the orthogonal subspace of the GHZ for each vertex here, and then I tensor this with the inverse of this sort of ferromagnetic projector on both sides. And then I do this locally around each vertex. So I have these four spins that interact with this one, this one, this one, and this one. Okay, so this is a kind of 8-body interaction. Not very nice, but it's like just an 8-body interaction, and then you sum over all the vertices around the torus.
Sorry, can you repeat 8-body interaction?
So because I have these four qubits in the GHZ state, they will interact with this one, this one, this one, and this one. So okay, so it's not a very nice formula, but you could write it in terms of Pauli matrices if you would prefer. It's not nicer because you have 8-body terms, so it's not nice. So in fact, it's in the end nicer like that. Okay, so we have 4n quantum bits. That's the size of the quantum system. Okay, that's my quantum Hamiltonian. Now, what I want is to investigate the ground state of this quantum Hamiltonian. And maybe the Hamiltonian is a bit artificial so that the ground state is easy to write down. So it turns out the ground state psi, which is shown on the graph gamma, is the tensor product of the GHZ over around each vertex And then you apply this kind of regularized ferromagnetic projector on the whole thing. So the ground state, you can picture of all these quadruples are entangled here, here, and here, and then you apply the ferromagnetic projector to all of them. Okay, so it's a sort of projection of these product of entangled states.
That's not easy to see, probably. This is the ground state.
It's not very difficult in the end. What happens is that this here, I give you an intuition. This here will kill the q minus 1 that was in the Hamiltonian. So these are the single terms in the Hamiltonian. The Hamiltonian is the sum of all these across the sum over the vertices. So q minus 1 times q, well, you feel that they cancel. And then this GHZ is orthogonal to 1 minus us, right? Okay. So it's kind of not so difficult.
Easy to verify.
Yeah, yeah, you can verify.
That's why he constructed it that way, of course. That's the idea.
Yeah, exactly. So this is a bit cheating. But you will see some other people constructed very similar states.
And they're very famous for it.
Yeah. Okay, what's nice about this state, in fact, is the following: that if you expand it in the computational basis, so these are just tensor products of zeros and ones or minus ones and plus in the string language. When you expand this in the computational basis, you find, okay, this is duplicated, well, not duplicated, but tensored 4 times because we have the structure with the 4 qubits around each vertex. And the coefficient of the expansion is a Gibbs weight at temperature beta over 2 divided by the square root of the partition function. And this Hamiltonian here, for my construction, is just the Ising Hamiltonian. Okay. Okay, and E minus beta over 2 is gamma. So gamma small is beta large, low temperature, pseudo temperature, gamma. And I care about gamma small. Gamma close to 1 is beta 0. Okay, so if you would do a measurement in the computational basis, the probability to get this classical Ising spin configuration is just the square of this thing. So E minus beta h divided by z. So it's the Gibbs weight becomes the quantum probability of getting the configuration S1, S2. Okay, this fact here is very closely related to the so-called PEPS states of Verstraete and Sirac, which are, well, I didn't write them here. Yes. What are the PEPS states? Just for your information, the PEPS state is almost the same state, except this is not tensored 4 times, strangely enough. PEPS stands for projected untangled pair states. How are they constructed? I take the same picture I had before, but now instead of untangling the 4 qubits, I untangle pair only. So it's a kind of dual construction. I untangle only pairs of qubits across the constraint. And then, so I use these Bell states, I do tensor product of Bell states. And then instead of my ferromagnetic projection, I do a kind of non-trivial not isometry, a projection of these 4 here onto a 2-dimensional subspace. So this is a somehow strange operation that maps C4 into C2. It's a 2 times 15, 16 matrix. It's not a square matrix. And you get almost the same state than the one I constructed.
I like your construction much better.
So, okay, so I can comment on that. I also like it more. I don't know. We discovered that, I mean, we're a bit ignorant, so we didn't know about PEPs, but anyway, we discovered it's there. Okay, so now, okay, turns out that if you have a circuit to construct a PEP state, as I have to here, by for each qubit of the PEP state, you create 3 other qubits. So you have this structure where you have tensor 4 times each qubit, and you use control node gates from a circuit for PEPs. You can construct a circuit for us. So if we can prove that our circuit has minimal depth log n, then PEPs will have minimal, cannot have a short depth also. And I'm not. People are trying to construct circuit for PEPs, and in fact, the depths that they come up with are much bigger than log n even. And I don't know if log n is the optimal depth or not. Okay. Now, of course, you could tell me maybe it's easier to show that the depth of PEPs is at least log n. Turns out that with our state it's easier to work with, but one could do both. Okay, so now let's forget the PEP state and let's take our state psi gamma, and let's look at the reduced density matrix and the global entanglement property of it, and then I'll come to the depth. Okay, so if you take a subset of 1 to n, okay, so a few qualifications. So there should not be the word any. This is a strict inclusion, and the subset should not contain the quadruples around each vertex. Okay. So the subset should not contain quadruples around each vertex. It can contain triples, or it can contain vertices anywhere you want, but never quadruple and not everybody. So, okay, I'm sorry that this slide, this is mathematically very imprecise.
Strict inclusions.
Sorry?
The inclusion should both be strict.
Yeah. And so this is, yes, it's not. Okay, then for these subsets, the reduced density matrix is diagonal. It's a combination of things of the type identities tensor Z. Z is the product of the Pauli Z matrix. So the matrix 1, 0, 0, minus 1, the 2 by 2, and you tensor it over the subset A. And here you tensor the identities over A minus B. Yeah, so I think it's B. Sorry, it should be a B. Okay. Then you sum over B, and this is the Gibbs average of the product of the spins in B. Okay, so a classical Gibbs average of temperature, inverse temperature. Okay, I use the standard notation. Okay, so the density matrices are very simple because they are diagonal. For PEPs, it's not true. They are not diagonal for PEPs. That's why it's easier to work with psi gamma. Now, you can construct states that are orthogonal to our states by introducing phase factors here, signs, and you can manage to construct many orthogonal states. And it turns out, so I introduced the phase factor in a correct way. I take any subset of qubits E such that the cardinality is odd, and I introduce phase factors for the qubits in capital E. It turns out that this is orthogonal to psi gamma. They are mutually orthogonal if the symmetric difference of two sets E and E prime is odd, and the density matrices are equal. Okay, so all these states here, at least if E is odd, the cardinality, they are locally indistinguishable. Okay, so there is lots of global entanglement in this system, a bit like GHZ. It's a bit like, okay, now I would like to come to the issue of circuit depth of these states. So I'll do exactly like I did for GHZ before. I will consider the density matrix of a pair of qubits. And if I compute this, I find this simple relation, the tensor product of two identity matrices for each qubit, plus the tensor product of the two Pauli Z matrices. Okay, so this whole thing is a 4x4 matrix. Each elementary matrix is a 2x2. And here the coefficient is the Gibbs average of SI SJ. So this two-point correlation at temperature theta. And I remind you, I am on the torus. I have periodic boundary conditions in the end for this Gibbs average. Okay, this thing here, first observation, it can be written as a convex combination with weights 1/2 of two simple products. So, and as long as this average, which is positive because of GKS inequality for a magnetic system, is positive, I can take the square root. As long as this is non-zero, I cannot collapse this to a single product. So it's a genuinely, it's a separable state, but a non-trivial one. And now, in fact, what happens in the small gamma regime, which is equivalent to low easing temperature, recall we have this long-range order for periodic boundary conditions. So if I take n to infinity first and I minus j to infinity after, I get the square of the magnetization, which is strictly positive. Okay, at small temperature, at high temperature, this would be 0, so it would not work. But at low temperature, so small gamma, this is strictly positive. So, okay, we have to revisit a bit the old papers because, well, we don't want to work at n infinity. Maybe Tony could help me out with the directly infinite system, but okay, quantum circuits, usually they are finite anyway. So if you take any pair of qubits at distance at least log n, then you still have that this pair correlation is m squared, the magnetization squared, plus little O(n) of 1, this tends to 0 when n goes to infinity. And the density matrix, you can write it eventually as this convex combination, non-trivial one, because m is non-zero. You see something related to a plus phase here, something related to a minus phase in the model, and the negligible term. The negligible term comes from, because n is not really infinite. So then you deduce from that if you compare the density matrix to a tensor product of a single density matrices, this will be, the norm will be always greater than m squared over 2, which is strictly positive. So this way you work a bit more and you show that this pair density matrix for any n large enough is always, and if I minus j is at least distance from log n, is always far away from a single tensor product. Okay, so basically that's the argument to show that the state cannot be constructed out of a circuit of depth smaller than log n. Okay, because then I use the light cone argument and I'm done. Okay, so you can extend this analysis beyond the ground state to any state that is close enough to the ground state. So that's the norm of the difference of these two vectors. If it's smaller than delta, for delta small enough, then you can show that the associated pair density matrix cannot factorize. It will be away from any tensor product with a single term. And this happens because of the long range order again, gamma is small or beta is large. And you can do this, in fact, for all pairs, basically. And this then we use the light cone argument in that dilemma. But the minimal depth to construct any approximate ground state is at least log n. So this is essentially the message of this talk. One word about situations where, so all this rests on the long-range order in the Ising model and periodic boundary condition. What happens, because there we have two phases, what happens in regimes or situations where you would have only one thermodynamic phase in the Ising model? So the first case is the case of small beta, high temperature. Well, then m of beta is 0, and if you look at my formulas that I had before, if you put m equals 0 here, this collapses to the identity times the identity. The identity, so this factorizes in a trivial single tensor product. So at n finite, you have this norm is small, so basically you have factorization. So in principle, you could have a short circuit if gamma is close to 1 or beta is small. Okay. If you take, instead of the torus, if you do the same construction, not on a torus, but on a system with boundary condition where the qubits, you force the qubits at the boundary to be in the up state or the 0 state, then it turns out that the pair density matrix contains the previous terms here with plus boundary condition for the Ising model, but then you have these two terms. With periodic, these two terms were not here because this average is 0 with periodic boundary condition. Okay, by symmetry of the Ising model. But now they are here, and if you look at this expression, what is nice is that this expression factorizes into a single term here, and then the correction involves this truncated correlation function. And if you have a unique phase, well, with plus boundary condition, this goes to 0, even at low temperature and high temperature. So with plus boundary condition in the same model, this is approximately factor up to correction, small correction. So in principle there, you could maybe find a short circuit. Okay, the trouble is that I cannot construct these circuits for you, and I've not found them in the literature for the PEP state or our state. Also, I think it's open. And okay, so the construction of the circuits, I think, is an open problem. Okay, so I would like to conclude for time basically with a few comments. So as I said, this low shallow circuit result is related to this existence of multiple phases of an underlying classical model. In the analysis of data, which is much more complicated than with the Ising model, a similar phenomenon happens. Okay, you don't have to know what is this picture. This picture just depicts that you have phases of this constraint satisfaction problem where you have many, the solutions of this constraint satisfaction problem shatter, and you have sort of multiple phases, not only a plus and a minus phase, but you have multiple phases with interesting classical phase transitions. This was used by this group. However, their proof in the end is much more complicated from the classical point of view, because they have to control this kind of picture, and also they use a lemma, but which was proved. This was a kind of breakthrough lemma, which is very nice, but more difficult to prove, which says that this Born probability, which is nothing else than the Gibbs distribution for us, when it has finite weight on separated solution phases of the constraint satisfaction problem, yeah, so this is completely, this is not a complete statement. There is a lemma that says that whenever this Born probability distribution has finite weight on at least two clusters in such CSP problems, then the circuit has to be of depth at least log n. I forgot to finish the sentence. Yeah, so I will not go through everything in this conclusion. That's my last slide. I would like to say that a few things are open. We would like to have the theorem for any psi that is low energy, in the sense that for a small enough delta, the energy is less than delta times n. Now, okay, in finite dimensional lattices, one can show this is impossible. The best you can ask is low energy, in the sense that psi h psi is less than delta times n to the power d minus 1 over d. In 2 dimensions, this would be square root n. To attain this, you would have to go to random graphs or so-called expander graphs. This is what is done in computer science. The approximate ground states that we have, they are low energy in this sense, but however, there exist low energy states. So think of the first excited state that might not be approximate ground states, because the first excited state will be perpendicular to psi gamma, and then the distance is square root. Okay, so these are open questions. But finally, I would like to say that in this construction based on the Calderman-Steenschor quantum error correcting codes, in fact, the local terms of the Hamiltonian, they commute between themselves. And this is not really satisfactory, because that's why, in fact, they can treat really the full conjecture. If the terms don't commute, like in case that, or in our case, then the techniques there are not enough. So I think there are still nice open problems. And I guess I'll end on this note. And again, happy birthday, Tony, and best wishes.